Now in this video, let us try to solve a very popular dynamic programming problem called as the longest increasing subsequence, often abbreviated as LIS. The problem statement is quite simple. You are given an array of numbers. Your task is to find the length of the longest increasing subsequence. Let's first try to understand what exactly is a subsequence. You can think of subsequence as number one, something that you derive from the original array. Number two, the order of the elements is the same. And number three, that you may delete some elements. Example, 3 to 13. This is a subsequence. Why? Because 3 to 13 is number one derived from the original array, and you have kept the order of the elements the same. 2 is appearing after 3, 13 is appearing after 2, and so the case here. And lastly, you have deleted some elements, which is not required, but in this case, let's say you have deleted 8, 7, 12, 1, and 5, 9, 10. By similar logic, 1, 5, 9 is also a subsequence, and 2, 12 is also a subsequence. You don't always have to delete the elements. So 3, 8, 2, 7 till 10, basically this entire thing is also a subsequence. Now with that being said, let us try to understand what exactly is an increasing subsequence. It's pretty intuitive. For example, we have 3 subsequences that we have picked up from our original array. Now you can see that 1, 5, 9 is an increasing subsequence. Why? Because 5 is greater than 1, 9 is greater than 5. And so the case here. So what the problem wants us is that out of all the possible subsequences that you can get from this input, you have to find the longest increasing subsequence. There might be some subsequences which are non-increasing. So you have to pick the increasing subsequences out of all the subsequences and then have to find which is the longest increasing subsequence among that. So this is the problem. Now before diving into the intuition, I want you to first understand these two things properly. First, our longest increasing subsequence starts somewhere, which is trivial. It has to start somewhere. It can start at index 0, it can start at index 1, 2, maybe 5, whatever. The thing is, it starts at some index. Okay? Let me represent that information by LIS_I, which means the longest increasing subsequence that is starting at the index I. Second, the overall longest increasing subsequence, something that we have to find, is nothing but the longest among all these. Now what is all these? By all these, I mean LIS0, LIS1 till LIS9. Out of all these, if we choose the maximum, that is basically the LIS that we have to find, which is something not very hard to convince yourself. It's something sort of that a global maximum is basically the maximum of all the local maximums, right? So what we are doing here is we find all the longest increasing subsequences starting at individual indices. LIS0, LIS1. Let's say we get that list somewhere, that this contains LIS0, LIS1. Then what we do is just pick the maximum amongst all these. That naturally is, the longest increasing subsequence of the entire array. So far, so good. So our problem is now that we just want to find what is the longest increasing subsequence starting at the index I. Because if we are able to find this value for all the indexes from 0 to 9, we very well know that our answer is definitely one amongst these. So we just take the maximum of all these sub-answers, you can say. So how will we find the longest increasing subsequence starting at the index I? The best way is through examples. Let's take an example of I is 1. What this means? Longest increasing subsequence starting at the index 1. Effectively, the one that starts at 8. Now, what is the longest increasing subsequence that is starting at 8? This is not very hard to convince yourself that the longest answer that you can get, which starts at 8, is nothing but 8, 9, and 10. You cannot get a bigger subsequence than this. So, longest increasing subsequence starting at 1 is 8, 9, and 10. Now, what is exactly 9 and 10 in this answer? This 9 and 10, if you think for a while, is nothing but the longest increasing subsequence that is starting at 9. So what this means is LIS1 is 1 plus LIS8, or starting at the index 8, or LIS starting at 9. Which somewhat makes sense, because if we know that 9 is the next element that we are going to pick after 8, then there is no good reason to pick any suboptimal increasing subsequence. We should always pick the longest increasing subsequence from that point, because our goal is to find the longest one. So what we are effectively doing here is we are trying to break this problem, finding the LISI, into some sub-problems. So let's now understand this very, very carefully. This is sort of the gist of the problem. The longest increasing subsequence starting at any index I, if you want to find this, maybe take an example. Let's say I is 1, the case that we have already looked. Now what we do here, if you want to find LIS1, let's look ahead and find all the elements that are greater than 8. Because we want to find increasing subsequences at the end of the day. So no point looking at elements that are less than 8. So from this point, or from I, let's look ahead and find all the elements that are greater than 8. So what they would be in this case? You can see that 12 is greater than 8. You can see that 13 is greater than 8. 9 is greater than 8. 10 is greater than 8. So looking ahead from 8, we have found 4 elements that are greater than 8. They are 12, 13, 9, and 10. Okay? So effectively, once we know that, let's say 12, 13, 9, and 10, they are the elements that are greater than 8, we just get their individual LIS values. So what is LIS4? The longest increasing subsequence starting at 12. What is LIS6? Starting at 13. What is LIS8? Starting at 9. And similarly here. So for all the elements that were greater than 8, we see what are their corresponding LISs. Because again, we don't want to look at suboptimal increasing subsequence. We want to look at the highest or the longest increasing subsequence. Okay? So once we know these sub-answers or these answers of the sub-problems, it's very easy to compute LIS1 or LISI. So LIS1 in this case would be nothing but like maximum amongst all these values plus 1. Why plus 1? Because we also want to include 8 itself, since the subsequence is starting at the index 1 or starting at 8. One more thing to keep in mind, when we were calculating LIS1, we were dependent on LIS4, 6, 8, 9. So effectively, if we want to calculate LISI, it's dependent on I plus something. Now, why am I emphasizing or highlighting this? Is because I want you to intuitively understand that if we want to find all the LIS values for all the indexes, all the Is, it makes sense to go from right to left when we are filling this array, because the left answers are dependent on the right answers. Now, this is pretty much the approach of this problem. Let's now actually try to run through and solve this problem by hand. So first, let us create the LIS array in which we'll store our LISI values or LISI answers. And as already discussed, let us move from right to left while solving this. Also, whenever we are calculating any LISI, we'll just follow these two steps that we already discussed in the last slide. So we'll just look ahead from this I, find all the elements that are greater than this corresponding ith element, and then see which amongst these has the highest value. Naturally, that would form a part of our longest increasing subsequence starting at I. Let's now use this approach to solve this problem by hand. We proceed from right to left. First, we want to solve for LIS9 or the longest increasing subsequence starting at 10. What is that? The first step, when we look ahead of 10, we find nothing. Now this means that the longest increasing subsequence is just that number itself, which is 10. Hence we put value 1 here. Let's now move to LIS8. Let's look ahead of 9, find all the elements that are greater than 9. 10. Now see what is the corresponding value of LIS at 10. It is 1. So LIS at 8, or the longest increasing subsequence, starting at the element 9, would be equal to 1 plus 1. This one is LIS of 9. So let's put 2 here. Similarly, for LIS7, the longest increasing subsequence starting at 5, we look at all the elements greater than or equal to 5 ahead of it. They are 9 and 10. Now, which amongst these has the highest LIS value? It is 2. Hence, we put 2 plus 1 here, which is 3. So let's put 3 here. For 30, when we look ahead, we find that there is no element which is greater than or equal to 13. Hence, 13 itself in singularity is the longest increasing subsequence at this particular index. So let's just put 1 here. From 1, when we look ahead, all these elements are greater than 1. So what we do is find the maximum among these LISs and then add 1. which would be 3 plus 1 or 4. For 12, only 13 is greater than 12. So the longest increasing subsequence starting at 12 would be 12 and 13, or 1 less 1. So let's put 2 here. For 7, 12 is greater than 7, 13, 9 and 10. Now out of these values, which is the highest value? You can see 2 is the highest value here. And you can choose either of these. So it doesn't matter. So let's put 2 plus 1 or 3 here. For 2, when we look ahead, all the elements are greater than or equal to 2 except 1. Now which amongst these have the highest value? 3. So we put 3 plus 1, 4 there. So let's put 4 here. Similarly for 8, looking ahead we find that 12, 13, 9, 10, all these are potential candidates because they all are greater than or equal to 8. Which amongst these has the highest LIS value? It is 2. So let's put 3 there. Last but not the least, when we look at the LIS 0 or the longest increasing subsequence starting at 3, we find that by looking ahead we find 8, 7, 12, 13, 9, 10 and 5 all are greater than or equal to 3. Now which amongst these have the highest value? Now it's easy to see that the highest value is 3. Doesn't matter, we can pick any option among these. So we will put 3 plus 1 or 4 at this place. That's pretty much it. Very, very close to the solution. And the last step that we have to do is just to take the maximum amongst all these values. So the maximum amongst all these values is 4. And hence, our answer, or the longest increasing subsequence overall, will be 4. This is the function that we have to fill in. This returns an integer, and this accepts an array as the input parameter. For simplicity, I am using the same input array that we have discussed in the examples. So without further ado, let's begin implementing. First, let's try to do some sanity check. A is null, or perhaps if the array is empty. In this case, there is nothing to look at, so we just return 0 here trivially. Next, we initialize our LIS array, which is our DP or like memoization data structure. So we call it the LIS starting at index and initialize it to the length equal to the array. Next, we declare our length of the longest increasing subsequence, which is effectively the overall answer that we have put it out. So for now, let's just initialize this to 0. As already discussed, we move from right to left. So let's write a for loop simulating that. Right means array length minus 1 or the last element. Left means till 0. We proceed from right to left. Now what do we do? We look at each of these individual elements and then see what elements ahead are greater than or equal to the array. When out of these, we find the maximum valid and then add 1. So simulating this or like translating this comment into code, it would mean mop up all of these ahead elements. J is simulating the ahead. We see if the array J is greater than or equal to array I. If this is the case, we just update 𝗹𝗼𝗆. So 𝗹𝗼𝗆 would be equal to the maximum. So that would be so we'll update our answer. So the length of the longest increasing subsequence would be equal to 𝐿𝑖 starting at I. Also, and this is because let's say we are looking at 30. Okay. There is no element ahead of 13 which is greater than 30. And because of this, whenever we enter this loop, we never run into line 28. So effectively what we are saying is that LIS starting at 13 would stay as 0, which is not the case because every element in singularity itself is an increasing subsequence. So whenever we look at any element, we know that it's going to be at least 1. The LIS starting at that element or that index is going to be at least 1. So we declare this here. Eventually, once we exit out of these for loops, we return the length of the longest increasing subsequence. Let's now try to run this in action. And this returns the length of the longest increasing subsequence to be 4. Now, just for cross-checking purposes, we can also try to print our LIS array and correspondingly match these individual answers with the answers that we have computed by hand. So let's go through this corresponding array one by one and just print the individual elements. I'm going to use print here. Let me call this as LIS and it's tool reformatting. Oops. I think this is print. Oops, my bad. Okay. So we have got this, which is pretty much what we computed by hand. Now let's try to see the complexity analysis of this problem. We'll see both the time as well as the space complexity. So first, let's try to understand what is the time complexity. Effectively, what we did in our algorithm is we have calculated all these individual LIS values from right to left. Now, while calculating any LIS value, let's say maybe like index 4 or 12, what we effectively do is we look ahead, find everything that is greater than this particular element, and then see their corresponding LIS. Seeing the corresponding LIS is constant time. Let's say if you want to see what is the LIS for 9, we have already computed that before. And we just get this value from this array. But whenever we are at an index and we look ahead to all the elements, it takes the time proportional to the length of this particular section. And this would vary for individual indexes. So example here, this would be time of, let's say, 5 units. because we are looking at 5 elements ahead of it and seeing which amongst them is greater than 12. Similarly, when we are at 7, we are looking at 6 elements. So for computing all the aliases from right to left, it would be like 0, plus 1, plus 2, plus 3, and so on till 9. This is for this, and this is for this. Effectively, what it means is, for any array of length n, we are summing 1 plus 2 till n minus 1, which is nothing but order on n square. So it takes time, order n square. Similarly, for the space complexity, we have just created another separate array for storing the aliases. And so the extra space that we have is order n. So the space complexity is order n. Now, before wrapping up this problem, I want to emphasize one of the key takeaways from this problem, which is nothing but this approach, or you can call it the pattern, where we say that the alias, or like whatever we have to solve, it starts somewhere. So we are representing that information by introducing indexes. So we are saying that if you want to calculate, let's say, longest increase in subsequence, we know that it starts somewhere. So why not just calculate all these somewheres separately and then take the maximum amongst them, which is this particular thing, for the overall longest increase in subsequence. So you just want to keep this in the back of your head when encountered with any dynamic programming problem in future, because this particular approach is also used in disguise in some of other similar problems. Hey everyone, in this video let us solve another popular interview problem called as the maximum length of chain of pairs. Now, just a disclaimer alert, this problem is actually an application of the longest increasing subsequence problem. So with that being said, let's move to the problem statement. We are given an input in the form of some pairs. What is a pair? A pair is nothing but an xy coordinate, where it is given to us that y is always greater than x. Now what we have to do, we have to return the length of the longest chain that we can form in the pairs. What is a chain? Chain is a sequence of pairs such that the first element of each pair is greater than the second element of the previous pair. Let's take an example. It is given to us that 15, 22, 17, 32, 38, and so. This is the input. All the pairs in the form of x and y, where y is greater than x, in all the pairs that you can see. Now let's see what exactly do we mean by a chain here. A chain is a sequence of pairs. So let's select any sequence of pairs. Let's say 17, then followed by 32, 38. Okay. Now this sequence follows the conditions for a chain. Why? Because the first element of the next pair is greater than the last element or the second element of the previous pair. So this forms a chain. Let's say we select maybe 49, 55, this one, followed by this one, 44 and 50. Now does this form a chain? The answer would be no. Why? Because the first element of the second pair or the next pair is less than the second element of the previous pair. By similar logic, it's easy to see that 17 followed by, let's say, 32, 38, then followed by 4450. This forms a chain too. Why? Because the first element of the next pair is always greater than the second element of the previous pair. For example, 32 is greater than 7, 44 is greater than 38. So in this way, we have to select the longest chain that we can form with these pairs. Now, for understanding the intuition for this problem, it is very important to understand what is the definition of a chain. So a chain is nothing but a sequence of pairs. Let's take an example. Maybe I choose 1, 7, followed by 15, 22, 32, 38, 49, 55. So as per the definition of the chain, this is a chain. Why? Because number one, it is comprised of the sequence of pairs. Number two, every first element in the pair, in each of the pair, is greater than the second element of the previous pair. So what I mean here is that 15 is greater than 7, 32, 22, 49 is greater than 38. Now therefore, this is a chain. Now if you look very closely, you will be able to observe that it is nothing but an increasing sequence of pairs. So pair 2, pair 1, pair 3, and pair 4. Pair 2 is greater than pair 1, this is greater than pair 2, and this is greater than pair 3. And when I say greater, I mean that the first element x2 is greater than y1. This is how I compare the pairs. Now what we have concluded so far is that a chain is nothing but an increasing sequence of pairs. What the problem wants us to find is the longest chain, the length of the longest chain rather. Now what is this longest chain? It means longest chain is an increasing sequence. So longest increasing sequence. In other words, we just have to find the LIS in this input. Awesome, right? Now how do we find the longest increasing sequence or the longest length of the chain? We just go by the same thought process. The longest chain would definitely start somewhere, okay? So it can start maybe at 1, 7, 15, 22, 49, 55, whatever. It can start anywhere among these pairs. Secondly, if you're able to somehow calculate the longest chain values for all of these cases, so you calculate the longest chain starting at 0, 30, you calculate the longest chain starting at this, 32, 38, for everything. Now definitely our answer is one amongst these. And that would be nothing but the maximum value amongst these, or the overall longest chain. So how do we find the length of the longest chain starting at I? In other words, for example, we take I1. So how do we find the longest chain starting at this index? Or how do we find the longest chain whose first element or whose first pair that occurs in that series is 1522? We look ahead and we find all the potential candidates. What does this mean? Find all the pairs that you can place after the ith pair. So the ith pair here is 1522. What can be placed after this pair? You can place a pair after this pair such that the x is greater than 22, right? According to the definition of the chain, which means that we can place 32, 38 here, 44, 50 here, and 49, 55 here. So we find all the pairs that can be placed after the ith pair. Now, amongst all these next pairs, which are the next pairs? 32, 38, 44, 50, 49, 55. Amongst all these next pairs, we choose the one that forms the longest chain from that point. For example, hypothetically, the longest chain that is originating from 30 to 38, or like starting at this pair, is 2. The longest chain starting here is 1. The longest chain starting here is 1. So we choose that particular pair as our next pair, which has the highest value. Now, one quick question in this regard. How do we find all the next pairs? Let's say we are maybe at I equal to 1, or we are calculating LLC 1. How do we find all the next pairs? Now, one initial solution that comes to mind is just iterate through this array, find all the other pairs, and see which amongst them can be placed after 1522. For that, we just see if the x is greater than 22, right? Now, this is not the most optimal way to solve this. Why? Because for every ith pair, what we are doing effectively is we are going through the entire array, and then for all the other pairs, we are choosing those pairs that have their x which is greater than the y of the ith pair. So essentially we are doing repeated comparisons. For this I, we are seeing all the pairs and then comparing these pairs with our ith pair. Similarly, when we go here and we calculate the LLC for this I, we are going through all other pairs and then again comparing with this pair. So the fact that we are doing pair comparisons, multiple pair comparisons again and again, should help us to click or give a thought that perhaps we can sort this array. We can sort all the pairs in our input array. And this would make our life way a lot easier. So let's see how that looks. Now here I have sorted these pairs by their start indexes or their x values. This is how it looks. Also, I have represented this visually here. Now for every individual pair that we are looking when we are calculating the LLCI, we don't need to look at all the pairs. We just need to look at the pairs that are ahead of that pair. For example, when we are looking at 2058, in this case, we don't need to look at these particular pairs because their start is already less. So we just look at those pairs that are ahead of my ith pair, which are these pairs. And again, when we are calculating the LLCI value, we are dependent on the answers ahead of me. So it makes sense to start filling this LLCI array from right to left, same as we did in the longest increasing subsequence problem. Now let's try to solve this problem by hand. Let's start with the index 6. For index 6, there is no pair that is next to it because it is our last pair in the series. So let's put 1 here. Let's move to the index 5. Looking ahead, we find all the pairs that can be placed after my ith pair. And there is no such pair. Why? Because 49 is not greater than 50. So you cannot place this pair after this pair. Hence we just put 1 again. Let's now move to index 4. Let's find all the pairs that you can place after index 4, which means all the pairs that have their x greater than 38, which would be 44 and 49. Now, which amongst them has the highest value? Both of them have the value 1. So you can pick either of these, doesn't matter. So let's put 1 plus 1 or 2 here. You're adding 1 because you also have to include this pair in our series from where we are starting. Let's move to the index 3. look ahead and find all the pairs that you can place after this pair. It's easy to see that there is no such pair that you can place after this, because there is no such pair with its x greater than 58. So we just put 1 here. Similarly, for 1522, look ahead. We find that 32, 38, 44, 50, 49, 55, all these can be placed after 1522. Now, which amongst them have the highest LLC value? It is this. So we put 2 plus 1 or 3 at this place. Similarly, for 17, we find that this is our potential next candidate. This is also our potential next candidate. In fact, everything is our potential next candidate. Now, which amongst has the highest value? It is 3. So we just put 3 plus 1 or 4 at this place. Last but not the least, when we look ahead of this, we find that 3238, 4450, and 4955. All these pairs can be placed after this pair. And which amongst them has the highest LLC value? It is this. So we just put 2 plus 1 or 3 at this place. Our eventual step, we just take the maximum of all the LLC-I values that we have computed. So our answer would be 4. So let's try to implement the approach that we have discussed so far. This is the length of the longest chain of pairs function that returns the integer or the length, and it takes in an input parameter of pairs. For simplicity and just for convenience, I'm choosing the same list or same list of pairs that we have discussed in our hands-on example. Let's try to implement. We can maybe start with some sanity checking. We can check if the pairs is not null or is rather null. And if this is the case, let's just return 0. Why we are doing this? Because in this case, the pairs is either empty or null. So it doesn't have any pair to pick and select the longest chain. So we just return 0. Next, let us rather try to sort the array. So let us try to sort the pairs, and we are sorting by their start indexes. Okay. Now let's declare or initialize a variable that stores our answer. Maybe we can initialize it to 0. Let's now traverse from right to left in this pairs. For every ith element or ith pair that we are looking, we know that the answer is going to be at least 1, which is that pair itself. Okay. So let's just initialize that to be 1. And let me also declare our memorization data structure here. Now we look ahead and find all the potential next candidates, and then choose the best candidate. What does it mean by best? That has the highest LLC value. So let me simulate this using J. Looking ahead from I plus 1 till the length, arrow.length, and then let's check if pairs first element, if the jth pair's first element is greater than the ith pair's last element. If this is the case, let's just update our LLC I value to be the maximum seen so far. And eventually, once we exit from this for loop, we know that 𝗪𝐿𝐶𝐼 is the maximum or the optimal value. So let's just update our overall answer to be the maximum seen so far. Once we exit these for loops, let's just return the answer. Let's try to see this in action. There we go. This code is pretty much the same as the length of the longest increasing subsequence code or the LIS problem code. It's pretty much following the same template, except this particular line, where we are sorting just to make it convenient for us to look ahead. Now, this is why I recommended that it's very important that we solve the LIS problem first and understand that properly, including the implementation, the approach, the logic, the intuition. That would make to understand all these related problems very, very easy. Let's now see the overall complexity analysis of this problem. We'll start with time complexity. In our algorithm, first, we have sorted the input array. That takes time of n log n, where n is the length of the array. Then, while calculating the 𝗪𝐿𝐶𝐼, or for any index I, when we were calculating the LLC, we were looking ahead and finding all the elements that can be our potential next candidate. This takes time proportional to the size of this. So if we sum up together, it would be nothing but 1 plus 2 plus 3 till n minus 1. This is for this and this is for this, where we look ahead for everything. This is nothing but order n log n for the sorting plus order n square. This is the overall larger value, so our time would be bound by order n square. For the space complexity, we have just created one data structure that is nothing but an LLC array that has the size equal to the size of the input array. So it is nothing but order n. Now in this video, let us solve another very popular dynamic programming problem called as the longest common subsequence. It is often abbreviated as LCS. Let's look at the problem statement. We are given two strings, S1, S2. For example, S1 is 𝗪𝗡_𝐹𝑟𝑡𝑥, S2 is 𝗪𝗡_𝑑𝑟𝑥. Now our job is to find the longest common subsequence of both the strings. Now let us first understand by what exactly is a subsequence. Let's take an example. A subsequence of a string X is a sequence of characters that you derive from the string X, where the relative ordering of the characters remains the same as that of the string X. For example, let's say the string is 𝗪𝗡_𝐹𝑟𝑡𝑥 or our string S1. And we pick the characters A, F, and T. Now this is a subsequence. Because number one, A, F, T, all these three characters are derived from S1. Secondly, the relative ordering of the characters in our subsequence and in our string is the same. So F appears after A, T appears after F, and so is the case here. Because of the same reason, A, T, F. This is not a subsequence. Because even though the characters are derived or are present in S1, like A, T, F, the relative ordering of the characters is changed. F should appear after A and T should appear after F, but that's not the case here. Now, this is a subsequence. What we have to find is the longest common subsequence. So for example, A, F, T. This is a subsequence of S1. You can see that A, F, T is also a subsequence of S2. So AFT becomes a common subsequence. And what is the length of AFT? It is 3. Now similarly, we have to find that subsequence. That is number 1, common to both S1 and S2. And number 2, the length of this subsequence should be maximum. Now there are only 2 things that can happen given 2 strings. Either our first characters match, which is the case here in S1, S2, or they don't match. These are the only 2 things that can happen. Let's look at this case first. That is, the first characters are matching. Now, if the first characters of both the strings match, there is no good reason to not include that character in our longest common subsequence. In other words, we should always include that character, that first matching character, in our longest common subsequence. It's very easy to feel this intuitively as well as prove it mathematically by contradiction. At the end of the day, since our aim is to find the longest common subsequence, we should always include this character because this always increases the length of the subsequence by 1. For example, if this is the case, this is S1 and this is S2. You can think of these symbols as different characters in a string. So in this case, the first character matched. So we have included this in the part of the longest common subsequence. What about the remaining? The remaining part, which is this, is actually the longest common subsequence of this section. So effectively what I am saying is that if the first characters are matching, the longest common subsequence is equal to the longest common subsequence of this part. Let me call this as subsection plus 1. Makes sense, right? Now what is this subsection? It is nothing but the string 1 that is going from index 1. This is the index 1, this is 0 till the end. And the string 2 going from the index 1 till the end. Right? So what I'm saying is that the longest common subsequence of the string 1 and string 2, or the string 1 going from 0 till the end, which is the complete string 1, but just I'm trying to represent it mathematically. So longest common subsequence of the complete string 1 and the complete string 2 is equal to 1 plus the longest common subsequence of string 1 from index 1 till the end and string 2 index 1 till the end. Just for representation purpose, we can get rid of the end part. because it's pretty much the same everywhere, and we can capture that just by the first index. So to simplify, LCS 00, which is basically 0 till the end and 0 till the end for S2 and S1. Basically LCS of the complete strings S1 and S2 is equal to 1 for this, plus the LCS which is the string 1 from the index 1 till the end, and the string 2 from the index 1 till the end. Now this is valid only when the first characters of both the strings are matching. Let's now take a look at the second case. The first characters of both the strings do not match. Now if the first characters in both the strings do not match, then overall there are only 3 types of situations possible. So let me try to visually represent this so it makes better sense. Let me say that this is the string 1 and this is the string 2. And the first characters are not matching. As you can see, string 1 starts with A, string 2 starts with B. Now if this is the case, there are only 3 types of situation possible. The first situation would be that our LCS contains A. Second situation would be that the LCS contains B. Third situation, the LCS contains neither A nor B. Now these are the only 3 things that can happen. The LCS cannot contain both A and B. Why? Because A and B don't match, and we are looking for a common subsequence. So only 3 things possible. Either our longest common subsequence or our answer is containing this A and not B, or we are containing B and not A, or we are containing neither. Now I have represented these 3 cases here. This is the case 1, where the longest common subsequence is starting with A and not B. Similarly, this is case 2, where now it starts with B and not A. And this is the case 3, where we are starting with neither. Now let's zoom in this particular case and try to see the pattern here. This is the type where our longest common subsequence is including this and not this. Our longest common subsequence is basically this one that I've highlighted. As you can see, it starts with this and is not including this. Now it's easy to observe that the longest common subsequence that we have to find for the input for the strings S1 and S2 is nothing but the longest common subsequence of this string and this substring. And why am I saying this? Because we are definitely excluding this character. So the longest common subsequence or our answer should be equal to the longest common subsequence for the string S1 and for the string S2, but from the index 1 till the end. So effectively my overall longest common subsequence in this case, where we are excluding this and including this, is nothing but the longest common subsequence of this and this. Now similarly for case 2, where we are excluding the first character in S1 this time. By similar analysis, similar logic, the longest common subsequence here, it's again easy to see that it's the longest common subsequence of this substring in S1 and S2. So LCS should be equal to 1 means that the string 1 is going from index 1 till the end. And this means we are capturing the complete string 2, or which is going from the index 0 till the end. Now let's take a look at the case 3, where we are excluding both the start characters. We are excluding the first character in S1 and we are excluding the first character in S2. Now this time, since we are anyways excluding these, I can safely say that my answer, or the longest common subsequence, it should be the longest common subsequence of these substrings. In other words, mathematically, we can say that longest common subsequence that we have to find, which is also the longest common subsequence, 0, 0. 0 implies we are going from 0 index till the last for string 1, or we are capturing the complete string 1. And 0 here implies same for S2. So the overall longest common subsequence is equal to the longest common subsequence of string 1 starting from the index 1 till the end, and string 2 starting from the index 1 till the end. Now these are the only 3 possibilities that can exist when the first character of string 1 and string 2 don't match. Because either we could begin with the first character of the string 1 and exclude the first character of string 2, or we can do vice versa. We can exclude the first character of string 1 and include the first character of string 2, or we could exclude both. Now there is one more observation that I would like you to make. There is actually no need to include this case separately. Now why am I saying this? What we are doing in this case is, in order to find the longest common subsequence, we are finding the longest common subsequence of both the strings starting from the index 1. So effectively, we are finding the longest common subsequence of this section. Now, if you take a look at the case 1 and case 2, where we are finding the longest common subsequence of this section and this section. Now, in these two cases, we are already including this particular section, right? Similarly for this one, if you take a look at this section, then this particular part or this particular section for the case 3, where we go from the index 1 till end and 1 till end, this is already being included in the case 2 as well as the case 1. So effectively, I can just eliminate this case. Whatever the results that I'm going to find from case 1 and case 2, they should be sufficient and they should already include the results of case 3 in them. So to summarize, when the first characters of both the strings do not match, we just need to handle two situations. Situation 1, where the LCS is equal to the LCS of this part, and situation 2, where the LCS is equal to LCS of this part. Now, since we want to find the longest answer, we would be taking the maximum of both of these possibilities. So to summarize, in this case, where the first characters are not matching, the LCS should be equal to the maximum of two possibilities, which are LCS 0, 1 and LCS 1, 0. Now, more generically, we can say that this should be valid for any I. Right now, we have looked at the 0th index. So, we have said that LCS 0, 0 is equal to 1 plus LCS 1, 1 for the case when the first characters match. When the first characters don't match, this equation holds true. Now, generically, this should be valid for any I. So effectively what I'm saying is LCS ij is equal to 1 plus LCS I plus 1 j plus 1, where I and j, they represent the indexes for the string S1 and S2. Consider this example itself. Now in this example, let's say my I is this and j is this. Now I and j, they are equal. So we can say that LCS I j, effectively LCS for the string S1 that is going from I till the end, and for S2 that is going from j till the end, is equal to 1 plus LCS of I plus 1 and j plus 1. So 1 plus the LCS of this part. Similarly, in this particular case, we can also say that when the characters don't match, when the ith and the jth characters don't match, then the LCS is equal to maximum of LCS I plus 1j and LCS I comma j plus 1. Now let us try to solve this problem by hand. These are my two strings, S1 and S2. We have to calculate LCS ij. Now based on the recurrence relation that we derived in the previous slide, we can see that it can be dependent only on three things. It can be dependent on the I plus 1, j plus 1 value when the characters on I and j match, or it can be dependent on I plus 1 j and ij plus 1. So if we see this visually or diagrammatically, and let's say we draw a two-dimensional array that is representing the LCS ij answers, then for any I and j, let's say I is equal to 1 and j is equal to 2, my answer to this particular ij can be dependent on I plus 1 j plus 1, can be dependent on I plus 1 j, or can be dependent on ij plus 1. So in order to get the answer to this particular problem, I need to get answers to these first. At the end, my answer would be LCS 0, 0. Why? Because I want to capture the LCS for the complete strings. And 0, 0 implies it goes from 0 till the last index and 0 till the last index. So with that being said, let us try to populate our LCS array from the bottom till the top and going from right to left. Because if we proceed this way, then we would be getting the answers to our sub-problems first, so we can easily compute the answer to our ijth value. Now one more thing, just for simplicity in calculation and to handle base cases more elegantly, I have appended both the strings by empty string. It shouldn't make a difference because this is the total string that is given to us and we just add an empty string to us. This is not a space, this is an empty string. So let's begin from here. Now what is LCS 7, 6? It means my S1 is starting from 7 till the end and S2 starting from 6 till the end. What is the longest common subsequence? Effectively of two empty strings. It's nothing but an empty string. So let's put 0 here. Now let's proceed here. What is the LCS of 7 and 5? For S1, this part, And for S2, this part, from 5 till the end, from 7 till the end. Now since an empty string is involved here, whatever string I bring in S2, the answer should be 0 because this is an empty string. So by similar logic, let me put 0 here. Again, it's easy to see that when we are filling for I is equal to 7, we are essentially taking this particular string from S1. So it's an empty string. So whatever string we take from this, be it 7.4, be it 7.3, be it 7.2, the answer is going to be 0. So let me put 0 here by similar logic. Now we move up and again proceed from right to left. So what is LCS 6 and 6? 6 here means we are going from 6 till the end, and 6 here means an empty string. So again an empty string involved here, but this time on S2. So whatever I pick in S1, be it 6, be it from 5, 4, 3, it should be 0 because the other side I have an empty string. So let me put 0 here. And by similar logic, I can put 0 in this complete layer. Now let us try to fill the remaining values based on the recurrence relation that we derived. So let us first fill LCS 6.5. What is LCS 6.5? It means the string 1, it starts from 6 till the end, and string 2 starts from 5 till the end. Now let us see which case this is. This time I is equal to 6 and j is equal to 5. Now the characters match, so it's case 1 because S1 I is S2j. Therefore LCS ij is 1 plus LCS I plus 1 j plus 1. So it's 1 plus this value. So let us put 1 here. Let's move to the next. What is LCS 6 and 4? So 6 and 4. Now at 6 and 4 my characters don't match. So this is case 2. So LCS is maximum of I plus 1j and ij plus 1. So it is maximum of this and this. So let me put 1 here. Let's take a look at this one. What is LCS 6 and 3? 6, 3. Now 6 and 3, x and d again don't match. So my LCS ij is equal to maximum of I plus 1j and ij plus 1. Maximum of this and this, so let's put 1. So let us now fill for LCS 6 and 2. So this is 6 and 2. Now again 6 and 2 characters don't match, so it's case 2. Hence we pick maximum of the right and the bottom. The right is ij plus 1. The bottom is I plus 1j. So the max is 1. Let us now try to fill this. LCS 6.1. Let's first mark the strings which we are taking a look. 6 and 1. Now 6 and 1 characters don't match. So again, the value here is max of this and this. Let's put 1. What is 6.0? It is represented by this. Now 6 and 0, they don't match. So our answer is maximum of this and this. So let us put 1 here again. Let's now move to our next layer and try to fill from right to left. What is LCS 5.5? Let's mark the strings 5 and 5. Now the characters don't match. So it's case 2. And hence we pick maximum of this and this. So let's put 1. What is LCS 5 and 4? So this is 5 and 4. Now characters at 5 and 4, they don't match. So it's again case 2. And hence we pick maximum of this and this. So let's put 1 here. What is LCS 5 and 3? Let's see. 5 and 3. So characters at 5 and 3, they don't match. So let's put maximum of this and this. So let's put 1. Let's take a look at 5, 2. 5, 2 is represented by these. Now the characters at 5 and 2 this time match. It is T. So it's case 1. And the answer would be 1 plus LCS I plus 1 J plus 1. So this is 1 plus this value. Let's put 2 here. Now what is LCS 5 and 1? 5 and 1. This time 5 and 1 don't match. So it's case 2. And hence we pick maximum of this and this. What is LCS? 5 and 0. So 5 and 0. The characters don't match. And therefore the LCS is maximum of this and this. So let's put 2. Now what is LCS 4 and 5? Let's first mark the strings 4 and 5. Now 4 and 5, they don't match. So it's case 2. This value therefore is maximum of this and this. Let's put 1. What is LCS 4, 4? Let us first mark the strings. Now 4 character in both match, which is R. So the answer would be 1 plus LCS I plus 1 J plus 1. So effectively 1 plus this value. Let's put 2 here. Now what is LCS 4 and 3? Let's first mark the string 4 and 3. Now 4 and 3, the characters do not match. So it's case 2. And therefore we pick the maximum of this and this. So we can put 2 here. Now what is LCS 4 and 2? 4 and 2. Now 4 and 2 characters do not match. So our answer is maximum of. So let us put 2. Now what is LCS 4 and 1? Now the characters at 4 and 1, they don't match. So it's case 2. And we pick max of this and this. Let us put 2. 4, 0. Now again, the characters at 4 and 0, they don't match. So it's case 2. And we pick max of this and this. Let's move to the top. And right to left. What is LCS 3, 5? So 3 and 5. Do the characters match? They don't. So it's case 2. And let us pick max of this and this. Let's put 1 here. What is LCS 3, 4? Do the characters match? They don't. So let's put max of this and this. LCS 3, 3. Now do the characters match? They don't. So let us put maximum of this and this. Now 3, 2. Characters match? They don't. Again, let's put max of this and this. What is LCS 3, 1? The characters match? Yes, they do. So this time it's case 1. So let us put 1 plus this value. So 3. Now LCS of 3, 0. So 3 and 0. Characters match? They don't. So let us put maximum of this and this. Let us put 3. LCS of 2, 5. So 2 and 5. Characters match? They don't. So it's case 2. So let us put max of 0 and 1. Just 1. What is LCS of 2, 4? So 2 and 4. The characters match? They don't. So let's put max of this and this, or 2. What is LCS of 2, 3? 2 and 3. Do the characters match? Yes, they do. So this is case 1. So let us put 1 plus this, or 3. LCS 2, 2. Let us mark the strings, see if the characters match, which they don't, so it's case 2, or the max of this. So let's put 3 here. LCS 2, 1. 2 and 1. Do the characters match? They don't. So let us put max of this and this. So let us put 3. 2, 0. 2 and 0. Do the characters match? They don't. So max of 3, 3, which is 3. Let's move to our top layer. What is LCS of 1, 5? So 1 and 5. Do the characters match? They don't. So let us pick max of this and this. Let's put 1 here. Now what is 1, 4? 1 and 4, the characters don't match. So we pick the maximum of 1 and 2. Let us put 2 here. What is 1, 3? The characters don't match again. So let us put the maximum of 2 and 3, or 3 here. What about 1, 2? Again, the characters don't match. T is not equal to C. So let us put max of 3 and 3 here. What about 1, 1? The characters don't match again. F not equal to C. So let us put maximum of 3 and 3. So let us put 3 here. 1, 0. Again, we have case 2. So the maximum of 3 and 3. Let's move to our first layer. What is 0, 5? 0 and 5. The characters don't match again. So let us put 1. Max of 0 and 1. 0, 4. The characters don't match again. So let us put maximum of 1 and 2, which is 2. 0, 3. The characters don't match again. So let's put 3 here. 0, 2. Again, let us put maximum of 3 and 3, which is 3. 0 and 1. Again, case 1. So let's put maximum of 3 and 3, or 3 here. And then last but not the least, 0, 0. This time the characters do match. So it's case 1. And the answer would be 1 plus 3. Let us put 4 here. Ultimately, we just return LCS 0, 0. That represents 0 till the end and 0 till the end. Essentially are complete strings. So we return 4, which is the answer. I have created a function called as the find the length of the longest common subsequence. It takes in the string s1 and the string s2 as input. It returns the integer, which is our answer, which is the length of the longest common subsequence. Eventually, I just print the length for cross-checking. And in this case, I have taken the same example that we were solving by hand. So let's begin. Handling some edge cases or corner cases. So let's check if +1 is null, or if the size of s1 is 0, or if s2 is null. We'll call it length, or the length of s2 is 0. If this is the case, we can trivially just return 0. If not, let's move ahead. Let's declare our data structure. So let me call the LCS, and let me declare it to be the length. So let me first get the length. So let me call length of S1 as M, and let me call the length of S2 as 1. And let me declare my two-dimensional array to be the size of M plus 1 cross M plus 1 plus 1 to take into account the empty string. Now let's try to fill our array, our LCS two-dimensional array, from the bottom to the top. And in every layer, we will move from the right to the left. So let's simulate this using code. So we will move from the bottom, which would be one length, or let me just call it m-1, I would have 0, and I minus minus. 2 is equal to n-1, j greater than or equal to 0, and j minus minus. Now there are only two possibilities as we discussed. Either the characters match or they don't. So this is the case when they match, and this is the case when they don't match. If they do match, then the answer would be nothing but 1 plus LCS I plus 1 and j plus 1. And if they don't, our answer would be maximum of ij plus 1 and I plus 1 j. Eventually, we just return 0, 0. That should be our answer for the complete strings. So let's try to run this and see what the result we get. It is full. In this video, let us take a look at another important dynamic programming problem called as the longest palindromic subsequence. Now this problem is actually very related to the longest common subsequence problem that we have solved. If not, I would encourage you to first go and solve the longest common subsequence problem and try understanding the approach, the intuition. And then solving this problem should be very easy and straightforward. So with that being said, let us move to the problem statement. We are given a string S. Our target is to find the longest palindromic subsequence in S. Now first, let us try to understand what do we mean by a subsequence. A subsequence, as already discussed in numerous other videos, is nothing but a series of characters that you derive from S. So a series of characters that you derive from S, and you keep the relative ordering of characters the same. For example, let's say I pick B, B, B and A. So this series of characters, it is derived from S, and the relative ordering is the same. As you can see, B is appearing after B, this B is appearing after this B, and A appears after B, and so is the case. If you pick, let's say, B, 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 A, and then A, and this is not a subsequence. Because even though all these characters are derived from S, that you can see here, the relative ordering of the characters has been changed. Because B appears after B, B appears after B, B appears after B, and so is the case. A appears after B, but this A appears prior to this A, and here it is appearing after this A. So this is not a subsequence. Now, our job is to find that subsequence which is first of all a palindrome. What is a palindrome? For example, B, H and B. So B, H, B is a palindrome. Because if you read it from this end, or even if you read it from this end, it should be just PHB. So it's essentially kind of symmetric. So we have to find a subsequence which is a palindrome and which is longest. So this is our task. Now let's take a look at the intuition for this problem. The intuition for this problem is very, very similar to the thought process that we used in the longest common subsequence problem. Let's see how is that. Now, our job or our final goal in this problem is to find the longest palindrome subsequence in a given string. So let's say my string is a collection of characters C1, C2, C3 till Cx. Now, if you think about this on a very high level, there are only two possible ways we can have this string. The first way is when C1 is equal to Cx, basically the first and the last characters match in the given string. Or they don't match. There is no other possibility. Whatever the string that is given to us, either my first and last characters can match or they don't match. Now, if my first characters and the last characters are matching, that is the case 1. So if this is the case that C1 and Cx, they are equal to each other. For example, in our input, A and A are equal to each other, the first and the last characters. Now, if this is the case, then there is no good reason to not include C1 and Cx in our answer. Why? Because it will only increase the length of the palindromic subsequence because they are equal to each other and they are on either ends. So we should always include C1 and Cx in our answer. And what would be the answer in this case? It would be the longest palindromic subsequence of this part, whatever that is, and then we add 2, one for this and one for this. So the longest palindromic subsequence of the entire string, and let me represent this by the first and the last index. So the first index would be 1 and the last index would be x. Basically this and this. So the longest palindromic subsequence of the entire string is equal to the longest palindromic subsequence of the substring of S, that is going from 2 till x minus 1, which is this, or essentially this part, and then we add 2. Why do we add 2? To include this and this character, which are equal to each other. Now it's very easy to feel intuitively and also to prove by contradiction that these characters, when they are equal to each other, they should always be a part of our answer. So effectively our answer would be the answer to this subproblem, and then we add 2. So let me write this LPS from 1x is equal to LPS from 2x minus 1 plus 2. 1 and x, if we talk about and if we think about more generically, we can use ing because this relation should conceptually hold true for any ing, not just 1 in x, if you think about it. So I can say generically LPS of the substring that is going from I till j should be equal to 2 plus LPS of the substring that is going from I plus 1 till j minus 1. Only if my Ci is equal to Cj. Only if my I and j characters match. Now let's take a look at the second case. What happens when my C1 and Cx are not equal to each other? So let's say this is A and let's say this is B, and they are not equal to each other. Now, if this is the case, I can never include this A and B in my answer. Why? Because we are trying to find the palindrome, and this would not look the same from both the ends. Essentially, it won't be a palindrome. So either we could include this A and not this B, or we could include this B and not this A, or we could include perhaps neither. What I'm saying is, either I can include C1 and not, or I can include CX and not C1, or I can exclude both. There are only three things that can happen. Now let's see what happens for this case first, when we are including C1 and excluding CX. So if you include this, or if C1 is a part of our answer and CX is not a part of our answer, what we are effectively doing is finding the longest subsequence of this part, because we are excluding CX anyways. So whatever remains, that is essentially giving us the answer. So to summarize, for the possibility 1, where we are including C1 and excluding CX, where the picture looks like this is being excluded, the answer is given by the answer to this substring from C1 till CX minus 1. So essentially, my longest palindrome subsequence for the string from 1 till X is given by the longest subsequence of the substring from 1 till X minus 1. I can more precisely say this as longest palindrome subsequence 1x is equal to longest palindrome subsequence 1x minus 1. Now what happens for case 2? Again, this is very similar to this case, but this time we are just excluding C1 and including CX. So this looks like including CX and excluding C1. Now the answer in this case is given by the answer to this particular section. So basically, the longest palindrome subsequence in entirety of my complete string is equal to the longest palindromic subsequence from C2 till CX when we are excluding C1. So the longest palindrome subsequence from index 1 till X, basically my complete string, is equal to longest palindrome subsequence from 2 till X, this particular substring. Now let's move to the third case, when we exclude both. Now by similar logic, if we are anyways excluding this and this, the answer is given by the answer to this part. So the longest palindrome subsequence from 1 till X of the entire string basically is equal to the longest palindrome subsequence from 2 till X minus 1. Only these three cases are possible when the first and last characters are not matching. If they are matching, the answer is given by this equation. If they are not matching, there are only three possibilities, and each individual possibility and its answer is given as follows. Now, if you think about little more on the case 2, especially on the possibility 3, where we are excluding both the characters, and our answer is given by the answer to this particular substring. If you think about this little more, you can say that there is no need to include this case separately, and it is already being taken care by these two cases. So let's see how. So first, let us again revisit what is the first and the second case. The first case is where Cx is not a part of our answer. So the answer is given by the answer to this subproblem. Now this subproblem in itself includes the answer to this subproblem. So any longest palindromic subsequence that I get from the index 2 till x minus 1 is already given by this answer, is already taken into account by this superset. Now similarly, the answer to the case 2, which is given by this particular substring, in itself includes this particular substring, which is the case 3. And so whatever answer that my case 2 gives should include the answer for case 3 too. And therefore there is no need to include this separately. So we can just eliminate this possibility, and there are only two things that remain. Now since our goal is to find the longest palindrome subsequence, when we look at the case 2 in entirety, the answer should be given by the maximum of this and this, right? Because only two things possible, the answer is given by this or the answer is given by this. So eventually, out of these two possibilities, take the maximum. So in other words, my answer should be the maximum of LPS 1 x minus 1 and LPS 2x. Now again, I have written this equation just for 1, 2, x and x minus 1 indexes. But by similar logic, as we were discussing here, this should be generically valid for any INJ, given that Ci and Cj don't match. More generically, if Ci and Cj, they don't match, the answer is given by the maximum of either this part, which is I plus 1 till j, or this part, which is I till j minus 1. So we take the maximum of these two. Because as we saw, these are the only two possibilities that can occur. The third possibility, where I and j both we are excluding in our answer, is already taken care by these two possibilities. Hence, we just take the maximum of these two. Now let's try to solve this problem by hand. First, I have drawn a two-dimensional matrix to represent the LPS INJ values. Now, if you think about how we should fill this two-dimensional matrix, first let us try to understand what is our recurrence relation and how we were using it to find the answer to our subproblems. Now, if you remember from the past discussions in the last slide, we saw that when the characters are matching, we take a look at the answer to this subproblem and just add. If they are not matching, we take a look at this answer and this answer and take the maximum from them. So what I'm trying to convey here is, if we want the answer to this part, we should have an answer to this part. Similarly, if we want to have the answer to this part, we should have the answer to this part. And so it continues till the very end, where we just have one single character in the string. And for that, we can just trivially return the answer as 1. Because H itself is a subsequence, is a palindrome, and is of the length 1. If we want to fill this two-dimensional array for all the subproblems, we should first try to fill all the base cases, and that would be the individual characters. So basically, I would proceed from the first layer, where I find the longest palindrome subsequence of the individual character strings. So I would find the longest palindrome subsequence of this, 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 and so on. And all of that would be 1. So basically, what is the longest palindrome subsequence of this? First of all, what is this? This can be said as the longest palindrome subsequence starting from 8 and ending till 8, because we are just taking a look at this thing. And what is this? This is 1. So we can put longest palindrome subsequence 88, which is this, to be 1. By similar logic for 77, 66, all the way till 00, we can put 1. Now let's move to the second layer. What is the longest palindrome subsequence of this? Now in this layer, we would see the answers for length 2 substrings. So we would take a look at this, and then this, then this, then this, this, and so on. So what is the longest palindrome subsequence of this? So basically, what is 𝗹𝗶𝗸𝗲? Essentially this value. Now this is the case 1 and this is the case 2. 𝗹𝗶𝗸 7 and 8. Now let us first see which case is this. I is 7 and J is 8. Now do the characters at 7 and 8, do they match? They don't. So this is case 2. And hence our answer is maximum of ij minus 1 and I plus 1j. So if this is ij minus 1 should be equal to this, and I plus 1j should be equal to this. So this is the maximum of this and this. So let's put 1 here. Now next, let us take a look at this. This is 𝗹𝗶𝗸𝗲 6, 7. Do the characters at 6 and 7 match? They don't. So this is case 2. And therefore, by similar logic, their answer is maximum of ij minus 1 and I plus 1j. So max of this and this, let us put 1 here. Let's move to this value now. What is 𝗹𝗶𝗸𝗲 of 5 and 6? Now do the characters at 5 and 6 match? No, they don't. So again this case, and therefore for filling at 5, 6, we take max of this and this. Let us put 1. Now let's move to this thing. Again the characters don't match, and therefore 𝗹𝗶𝗸𝗲 4, 5 should be equal to max of this and this. So let us put 1. Now let's move to this particular case. The characters again don't match, so the answer is max of this and this. So it is 1. Now let's move to 𝗹𝗶𝗸𝗲 2, 3. Characters don't match, so let us put 1. Let's move here. The characters again don't match, as you can see. So let us put max of this and this, or 1 here. Let's take a look at this length 2 string, which is the last one. The characters again don't match, so let us put the maximum of this and this for 𝗹𝗶𝗸𝗲 0, 1. So I'll put 1 here. Now let's move to our next layer, which is effectively we are trying to fill all the answers to our 3 length substrings. So first we'll take a look at this. We can actually proceed from the front or from the back. It doesn't matter. But I can proceed from the back since I'm anyways doing it for the first 2 layers. So the answer to this would be 𝗹𝗶𝗸𝗲 6 and 8. Now do the characters at 6 and 8 or I and j, do they match? They don't. So the answer would be the maximum of ij minus 1, I plus 1j. So basically this particular answer, which is the answer to 6 and 8, would be maximum of this and this. So let us put 1 here. Now let's move to this, which is 𝗹𝗶𝗸𝗲 5, 7. The characters don't match. So the answer to 5, 7 would be max of this and this. So let us put 1. Let us now move to 4, 6. Now this time the characters do match. So it is case 1. And therefore the answer would be 2 plus the answer to 𝗹𝗶𝗸𝗲 I plus 1, j minus 1. So effectively the answer would be 2 plus the answer to I plus 1 and j minus 1, which is this particular thing. So let us put 3. Now let's move to 3, 5. The characters don't match, and therefore the answer is max of 1 and 1. Let's move to 2, 4. The characters again don't match, and therefore the answer would be maximum of 1 and 1. So let us put 1 here. Now let's move to 1, 3. Characters don't match, and therefore the answer is max of 1 and 1. So let us put 1 here. Last but not the least, let's move to 0, 2. Again, the characters don't match and the answer is max of 1 and 1. So let's put 1. Let's now move to our next layer. Now next layer is for all the strings that are of length 4. All the substrings that are of length 4. Let's take a look at this one first. The characters don't match and therefore the answer would be maximum of 1 and 1. So let us put 1 here. For this one, which is our next, the answer would be maximum of 1 and 3 because again the characters don't match. Let us put 3. For this one, which is 3 and 6, which is 3 and 6, the answer would be maximum of 1 and 3 because B and H are not equal to each other. So let's put 3. For this one, which is 2 and 5, effectively this. Now this time our characters do match. Therefore the answer would be given by this particular equation, which is 2 plus LPS I plus 1 J minus 1. So this is 2 plus answer to I plus 1 J minus 1, which is this. So let us put 3 here. Now let's move to 1, 4. Again the characters match. So this is case 1. Answer is given by 2 plus the answer to this. So let us put 3 here again. Let's move to 0, 3. The characters don't match and therefore the answer is given by max of 1 and 1. Let us put 1 here. Let's move to this layer now. We are taking a look at all the substrings of length 5 now. So let us take a look at 4 and 8, which is basically this one. Now the characters don't match, therefore the answer is max of 1 and 3. Let us put 3 here. Now let's move to 3 and 7, which is this. This time the characters do match, therefore the answer is 2 plus answer to this. So let us put 5 here. Let's now move to 2 and 6. The characters don't match and therefore the answer is given by the max of 3 and 3. Let us put 3 here. Let's move to 1 and 5. The characters don't match. Therefore the answer is given by a max of 3 and 3. Let's put 3 here. Let's move to 0 and 4. Characters don't match. So let's put max of 1 and 3 or 3 here. Let's move to our next layer for length 6. So 3 and 8. The characters don't match. So the answer is given by max of 3 and 5. Let's put 5 here. Now let's move to 2 and 7. The characters don't match and therefore the answer is given a max of 3 and 5. So let us put 5 here. Let us move to 1 and 6. This time the characters do match and therefore the answer is 2 plus 3 or I plus 1 J minus 1. Let us put 5 here. Now let us move to 0, 5. This time the characters don't match again. So the answer is max of 3 and 3. Let us put 3 here. Let's move to our next layer where we'll take a look at all the length 7 strings. The first is 2, 8. The characters don't match and therefore the answer is given by maximum of this and this. Let us put 5. Let's take a look at this, which is 1, 7. The characters don't match, so the answer is max of 5 and 5. Let us put 5. Let's move to 0, 6. The characters don't match and therefore the answer is given by max of 3 and 5. So let us put 5. Let's move to our next layer, the second last layer, which is 1 and 8. Now this time the characters again don't match, so the answer is given by max of 5 and 5. Let us put 5 here. For 0 and 7, the characters don't match again, so the answer is max of 5 and 5. Let us put 5 here. Lastly, let us fill this, which is 0, 8, which is effectively what we have to solve for. Now, the characters are matching in this case, And therefore, the answer is given by this relation. So let us put 2 plus the answer. Eventually, we just return the overall answer or the overall longest palindrome subsequence of the string. And what is the string? That is going from index 0 till 8. So we return LPS 08 as our final answer, which is this. I've written a function that returns the length of the longest palindromic subsequence. It takes in the input of a string and returns the integer as the output. I've taken the same input that we were discussing in the examples. Eventually, I just return the length of the longest palindromic subsequence. For cross-checking, I just print it here. So let us first implement the base case. Let us check if the string is null or if the length of the string is 0. If this is the case, let us just trivially return 0. Else, let's move forward and let's create our LPS data structure to store the answer to our subproblems. Let me first get the length of the string in a variable, so I can conveniently use this ahead. Let us now come to the core business logic. Let us try to fill the LPS array from the palindrome of length 1 till the palindrome of length that is equal to the length of the string. So let us first fill all the size 1 palindromes, then the size 2 palindromes, till size n palindromes. So let me run a for loop and create a size variable that goes from 1 till length. Now in every iteration, let me walk through different substrings of the size equal to size. Let me mark them by the indexes I and j. So for example, when the size is 1, the first substring that I am going to take a look starts at 0 and ends at 0. So this should go till j is less than length. Now let's handle the base case first, whenever I is equal to j. If not, we can use our recursive relation to calculate the answer. So if the characters at I and j match, then our answer should be equal to 2 plus the answer to I plus 1, j minus 1. Else, it is equal to I plus 1 j. Eventually, we just return and hopefully we should get the answer that is equal to 7. Now let us try to see the time and the space complexity for our algorithm. Now it's very easy to analyze the time and the space complexity because effectively what we did while solving the problem is that we first constructed this 2-dimensional array, and after that we just filled this 2-dimensional array based on the recurrence relation that we derived. Now there are order n cross n or order n square entries in this 2-dimensional array, and n is the length of the string. So effectively we have order n square entries in this 2-dimensional array. Every entry when we fill, it takes time, which is constant because we are just using the answer to our already computed subproblems. So the total time taken in this case would be order n square. Similarly, for the space complexity, we can say that the only extra space that is being consumed is by this particular 2-dimensional array. And what is the size of this 2-dimensional array? It is order n square. So order n square is basically both the time and the space complexity. Now in this video, let us take a look at very important interview dynamic programming problem, that is called as the edit distance. Now the thought process used in this problem, just a disclaimer alert, is very similar to the thought process that we used in the longest common subsequence problem. So I would recommend to solve that first and understand that properly. And then going through this problem, the solution should be a piece of cake. So with that being said, let's begin. We are given a couple of strings, S1 and S2. Our job is to make these strings equal to each other. How can we do that? With minimum number of operations. Now what is an operation? We can either insert a character, delete a character, or replace a character. And these operations are only allowed on the string one, this string. Let's take one example to understand everything properly. Here, the string 1 is Golden's, the string 2 is Clyde's. Let's see one possible way using these operations on the string 1 to make them equal. We can just ignore G, it is already equal. This O, we can replace it with L. This L, we can replace with I. We can leave D as is. We can leave E as is. We can delete this N. And the string would then become equal to S2. So 𝗀𝗵𝗿𝗲, Clyde's. Now how many operations we did here? We did 4 operations. Now this is not just the only way. Perhaps we can, let's say, delete O. We can then insert I between L and D. And then we can just delete N. So this would also make it Clyde's. It should be equal to this. How many operations we did here? 3. Similarly, there might be other ways. Our goal is to find that way which involves minimum number of operations. Now let's take a look at the intuition for this problem. The intuition for this problem is again very similar to the longest common subsequence problem. So I would encourage to revisit that again to fully understand, and then going through this thought process should be very easy to follow. So let's begin. Overall, when we look at the string 1 and string 2, let's say string 1 is C1, C2 till Cn, and string 2 is C1 dash, C2 dash till Cn dash. Now overall, when we look at these two strings, there are only 2 possible things. Either C1 is equal to C1 dash, or C1 is not equal to C1 dash. Basically, either the first characters match of first characters, or they don't match, right? In the given example strings, for instance, the first characters match. But we could also have an input where the first characters don't match. For example, if this G in S1 would have been X, then our first characters won't be matching. Now let's first zoom into the case where the first characters were matching. Let's see how we should think about it, and how we should approach the problem. Now it's very easy to see that if the first characters of both the strings are matching or they are equal to each other, then actually there is no need to do anything or any operation. Because these characters, since they are already equal to each other, they are not causing any mismatches. So we don't need to do any operation at all. So we keep them put just as is. And then what remains? This particular parts. So string 1, that is going from the index 1 till the end, and the string 2 going from the index 1 till the end. So basically, the answer that we have to find for the overall string is nothing but the answer to this particular part. Because the first characters are already equal to each other, so we can just put them as is. Mathematically, if I describe edit distance, let me call it ED, of the string 1 and string 2, something that we have to find in this question, would be equal to the edit distance of the string 1 going from index 1 till the end, and of the string 2 going from index 1 till the end. Now this one is also basically the string 1 going from 0 till the end, and this is also going from 0 till the end. So I can just to simplify this equation, let me get rid of the end parts because it's clear in itself. So I can say ED of 0, 0 is equal to ED of 1, 1. In fact, if you generically think about it, let's say we want to find the edit distance for any string that is going from I till the index end, and for any string S2 that is going from the index J till the end. For example, if this is I and this is J here. Now if C3 is equal to C3 dash, this equation should hold true. So we can say that ED of IJ, when the character of the string 1 at I is equal to the character of string 2 at J. If this is true, then EDIJ is equal to ED I plus 1 and J plus 1. So generically, we can say that for any string S1 that is going from the index I till the end, and for any string S2 that is going from the index J till the end, we can say that ED IJ is equal to ED of I plus 1 and J plus 1 when the character of the string 1 at I is equal to the character of the string 2 at J. Now let's take a look at the case 2. In the character 1 of both the strings, the first character, they don't match. Now in this case, if there is a mismatch, what can we do to make the strings equal to each other? Now according to the problem, there are only three things that we can do on the string 1. We could delete the character, we could insert a character, and we could replace a character. Now let's see these cases one by one and see how our solution unfolds in these three cases. Now let's take a look at the case 1 where we delete a character. Let's take one example. Maybe we have the string 1 as, let's say, ABC, and the string 2 as PQR. Now, the first characters are not matching, and we have opted for deleting the character from the string 1. So we delete the character, the first character A. So what remains? The string 1 from index 1 till the end, and the string 2 from index 0 till the end. So overall, our answer would be 1 for the operation deletion, where we deleted the character A, plus the answer to the remaining part, which is the string 1 from index 1 till the end, and the string 2 from index 0 till the end. So mathematically, I can say that in this case, the array distance of the strings would be equal to 1 plus array distance of the string 1 from index 1 till the end, and the string 2 from index 0 till the end. Again, same as here, this is generically valid for any INJ. Now the second case, when we insert a character in the string 1. Now when we insert a character, first of all, we will only insert a matching character of the string 2, because we want to make the string 1 and string 2 equal to each other. So if the first character of the string do not match, and we have opted for inserting the character, we will insert the matching character of string 2, which is P, at this place. So my first string would become PABC, and the second string would be PQR. Now after insertion, these characters are now matching, P and P. Now what remains? This part and this part. Now what is this part? Mathematically, it is the string 1 that is going from the index 0, because we have inserted P prior to A. So this is index 0 till the end, but string 2 is now indexed from 1 till the end. So mathematically, I can say that array distance of my strings here, when we have opted for insertion, is equal to 1. 1 is for insertion, plus my answer to array distance of 0 and 1. Now the third and the final case is when we replace the character of the string 1. Again, let's understand with this example. Now the first characters are not matching, A here and P here, and we have opted for replacing the character of the string 1. So we just replace this A by P. After this replacement, the first characters are matching. Now what part remains? This and this. What are these mathematically? String 1 from index 1 till the end, string 2 from index 1 till the end. So I can say that array distance of string 1 and string 2 completely, 0 till the end and 0 till the end, would be equal to 1 one for replacement of the first character of the string 1 plus array distance string 1 from index 1 till the end and string 2 from index 1 till the end. Now these are also valid generically for any ing like this that we have discussed. So in a nutshell, when the characters mismatch, there are only 3 things that we can do, 3 operations as per the question. Delete character, insert character and replace character for the string 1. Now since we want to find the least or the minimum number of operations, therefore it makes sense to take the minimum of these 3 possibilities for our optimal minimal answer. So essentially what I'm saying is that ed00 should be equal to minimum of 1 plus ed10, 1 plus ed01 and 1 plus ed11. Basically I can take 1 as common, so my equation becomes minimum of ed01, ed10 and ed11 plus 1. So we take the minimum of these 3 and then add 1. So this is the equation that we use when the characters mismatch, and this is the equation we use when the characters match. Generically they are valid for ing, this one as well as this one. So let's try to solve this problem by hand. I have written the recurrence relation that we have derived in the last slide. This is the case when the characters are matching. This is the case when the characters do not match. Here is the string 1 and here is the string 2. Also, I have appended both of these strings by an empty string. Again, they are just empty strings and they shouldn't change our string 1 and string 2. But they will make our calculation very easy. You will see how. Now one more thing. Whenever we want to calculate the answer for any ig, we can be dependent on I plus 1 j plus 1 based on this equation, or we can be dependent on I plus 1 j, or we can be dependent on I and j plus 1. So we will try to fill from the bottom to the top and then from right to left, so that we have answer to our sub-problems first before we get the answer to our main problem. So let's begin. First, when both of these strings are empty string, this case. Now in this case, we actually do not need to do anything. The strings are equal naturally since they both are empty strings. So we just put 0 here. Let's first fill this particular row. This represents when S1 is going from the very last index, which is the empty string. So basically this represents an empty string for S1. If you want to fill this particular entry here, what it means? It means the array distance for this empty string and for this substring of S2 that is going from S till the end. Now in this case, we would have to delete S in order to make these strings equal. So the answer would be 1 here. or one operation. Similarly, here again we have this as an empty string and then 2 characters here in string 2, the substring of the string 2, that is going from E till the end. And the only option to make them equal to this empty string is to delete these characters. So effectively, I'll put 2 here. Similarly, it's very easy to see that there should be 3, 4, 5, and 6. By similar logic, we can fill this column, which now represents S2 being the empty string and S1 being the strings from S till the end, from N till the end, E till the end, and so on for these individual entries. Now, if you want to fill this, what does this mean? S2 is an empty string. S1 is the string or the substring precisely going from S till the end. So in order to make this equal to this empty string, we would have to delete S. That is the least number of operation that we have to do. So it should be 1. So let me put 1 here. Similarly, here it means an empty string and then 2 characters. So we have to delete these 2 characters anyway to make these strings equal to each other. Those are indeed the least number of operations. So I put 2 here. It's easy to see that this should follow naturally. 3, 4, 5, 6, 7. Now let's try to fill our remaining part. Let's proceed as discussed from the bottom to top, and in every particular row, let's move from the right to the left. Let's take a look at this case first. Here, this means the string S2, which is going from S till the end, or this particular substring of S2, and this particular substring of S2. Now, for ij, basically, I is this and j is this. Let's first see which is the case. Is it this one or this one? Now you can see that the characters match here. And therefore it's this case. What is the answer in this case? It is the answer to I plus 1 j plus 1. So it is this. Which is also something that we can see because both of these are equal to each other. So we put 0. Let's move here. Let's take a look at the I and j characters. Are they equal? No, they are not equal. So is this case. What is the answer in this case? It is the minimum of I plus 1 j plus 1, I plus 1 j, and I and j plus 1, and then we add 1. So the minimum of these 3, which is 0, and then we add 1. So it becomes 1. Let's move to this. The I and j characters S and D do not match. So again, by the same logic, we take the minimum of these and then add 1. It should be 2. Here, the characters again don't match. Take the minimum and add 1, which is 3. 2 plus 1. Here, characters again don't match. So we take the minimum and add 1. So it should be 4.
2,000 years later.
G and G do match. So let's put this just 3. Eventually, our answer for the complete string S1 and the complete string S2. By complete, I mean going from 0 till the end and 0 till the end. So overall answer would be ED of 0, 0. And therefore, the answer is 3. I have created a function called as the calculate error distance. It takes in the input of 2 strings and returns the answer. I have taken the 2 strings the same that we were using in the examples. Ultimately, I just print these 2 strings for cross-checking. First, let me try to grab the length of the individual strings so that I can use them conveniently later. Let me call them length 1 and length 2 to be the lengths of string S1 and S2 respectively. Next, let me create the DP data structure. Let me call it ED, the same as we were doing in the examples. So that should be equal to the number of rows should be equal to length 1 plus 1, and the number of columns should be length 2 plus 1. I'm using plus 1 to signal or to take into account the empty string. Next, let us try to fill our base case. Now, when there are empty strings for S1 as well as S2, which is basically ED of length 1 and length 2, we just put 0 because we don't need to do any extra operation here. Next, let's fill our base case for the bottommost layer, the layer in which the string 1 is empty. So if the string 1 is empty, we just have to delete all the characters of the string 2 to make them equal. So let me try to write a for loop. Effectively, what I'm doing in for loop is pretty much the same that we saw in the example. I'm trying to fill it from right to the left. I'm trying to fill the bottommost row, which is basically ED length 1. And then I'm adding the rightmost or the next or the immediate right answer plus 1. Plus 1 is to delete this character that I'm looking at, which is basically the J. And then this is my answer that I've already computed. So you might recall the bottommost layer when we were doing the example, we filled from 1, 2, 3 and till the length of the string 2. So this is pretty much doing the same thing. Effectively, just to summarize, I wrote a comment. When the string 1 is empty string, there is only one choice to make in order to make the two strings equal. And what is that? To delete all the characters of S2. So therefore, this will fill from 1, 2, 3, 4 from right to left. By similar logic, let's fill the rightmost column. It's pretty much the same as this, but the only difference here is S2 is an empty string. So there is only one choice to make, and that is to delete all the characters of S1. So I've done pretty much the same here. I've moved from the bottom to the top, and I've filled the rightmost column, which is length 2. Now, let's try to fill the values for our remaining matrix using the recurrence relation that we have derived. So basically, I can say that for int I is equal to length 1 minus 1, length 2 minus 1, now there are only two possibilities. The length, or rather the characters at the index ing match or they don't. Let's say they are matching. If they match, my answer should be equal to I plus 1 and j plus 1. In this case, my answer, when they are not matching, when the characters do not match, it should be equal to 1 plus minimum of EDI plus 1j EDI plus 1j plus 1 and EDI j plus 1, all the three values. Ultimately, we just return ED00 as our answer. Now let's try to run this and see what is the answer that it gives us. It is 3. So let's look at the complexity of the approach that we have discussed. Let's first take a look at the time complexity. Now in our approach, we have filled all of these entries of the matrix. Let me call the size of S1 to be maybe M, and size of S2, let's say it's N. Then we have basically filled M cross N entries. And what is the time that we took to fill each individual entry? It is constant. Why? Because the answers to our sub-problems were already computed before, and we just plugged in their values whenever we try to fill in any entry. And this is actually because we tried to fill this matrix from the bottom to top and from right to left. So we followed the right ordering when we were actually filling this DB matrix. So effectively, coming back to our time complexity, what is that? It would be order Mn and order 1, which is basically order Mn. Space complexity is again very straightforward to see. We just have a matrix, extra matrix constructed. What is the size of the matrix? It's order Mn. So this is both the time and the space complexity. M and N are the length of the strings. In this video, let us take a look at another popular dynamic programming problem called as the buy and sell stock. The input is a day-wise prices of the stock. So let's say we have a stock, and then these would represent what are the daily prices of this stock. So let's say on day 0 it is 8, on day 1 it is 3, and so on as the day progresses. So this is the input that is given to us. What is our job? We have to find the maximum amount of profit that we can make being a trader. What are the conditions? First, we should hold at most 1 share of stock. So let's say I'm a trader. I purchase the stock on, let's say, this day, and then sell the stock on this day. So I make a profit of 15 minus 8, which is nothing but 7 units. Now let's say if I would have bought 2 shares of this stock, then I would have made a profit of 15 into 2 minus 8 into 2, which would be 14 units. So this is not allowed, because we can hold at most 1 share of stock. Okay. Second, we can make multiple transactions. What does this mean? A transaction is a buy and sell. So let's say I purchase 8, then sell 9. Then I again purchase on this day, and then I sell. So I have made 2 transactions here. So this is allowed. Like there is no compulsion to just make 1 transaction of X number of transactions. You can make as many transactions as you want. Now let's take a look at the intuition for this problem. First, let us take a couple of examples. Let's say I am a trader, and in order to maximize my profit, I try to make these 2 transactions. Or like this is my strategy. Now see what does it exactly look like. This means that I have bought the stock on day 0, I have held the stock on day 1, I have sold the stock on day 2. Okay. Then for the next day, I have ignored this. For the next day, I have bought the stock again. The next day, I have held the stock. And then finally, I have sold the stock here. So it looks like this thing. B represents buy, S represents hold, S represents sell, and I is ignoring. Now another trader comes and he makes these two transactions in order to maximize his profit. What does it look like? Similarly, we can see for the day 0, he has just ignored this. For the day 1, he has bought the stock. Then he has sold the stock on day 2. Next day, he has again bought the stock. Then he has held the stock on day 4, sold it here, and then finally ignored it. Now, why am I telling you all of this? It is because I want to emphasize the fact that given any trader and whatsoever transaction he takes, let's say he does T1, T2, T3 till Tn, whatever this is, you can just represent it in a series of B, H, I, and S. Just buy, held, ignored, and sell. Because these are the only possible actions that we can do on any given individual day. There is nothing else that you can do apart from these. Either you can buy the stock, either you could sell the stock, you can hold the stock, or you can ignore that day. There is nothing else you can do apart from this on any given day. Now, we very well know that whatever strategy that the trader can take or whatever transactions that he makes, they can be represented by a series of B, H, S, and I. Now here, I have enumerated all these possibilities. Essentially, all the permutations of B, H, S, and I. So these are the permutations that are starting with B. These are the permutations starting with I. These starting with S. And these starting with H. So basically, whatever strategy that any trader is taking, it should lie somewhere in this superset. So effectively, we have to find that strategy here that yields the highest profit, right? Now, in order to find the overall best strategy in this set, let's try to find the best strategy here, 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 here. Let me call them best 1, best 2, best 3, and best 4. And then eventually take the maximum or the overall best. So effectively saying that, give me the best value given that the strategy is starting with B. Then give me the best value given that the strategy starts with I. Similarly, give me the best value, the strategy starts with S. And give me the best value given that the strategy starts with H. And then I am going to take the overall best among these 4 sub-best answers. It's essentially the same thing. So we are trying to find the local maximum here. Then we are trying to find the local maximum here, here, and here. And then for global maximum, we are trying to take the max of all these. Now let's see how can we find the best value here. Now first of all, what is this? This is a set where my first move in the strategy is starting with buy. Now let me represent this mathematically. Now give attention to this part. Let me say BI represents the maximum profit that a trader can make from the ith day till the end, given that there is D on the ith day. In other words, BI means that it is given to me that I have bought the stock on the ith day. Then tell me what is the maximum profit from that day till the end. So, if I have to find the best in this set, it means I have to find B0. Why? Because B0 means the maximum profit that I can make from the 0th day till the end, given that I have bought the stock on the 0th day, which is the case here. I have bought the stock on the 0th day and I have to find the maximum profit from the 0th day till the end. Up with me? Now our goal is to find B0. Let's see how can we find B0. But before that, I have a quick question for you. Let's say I have bought the stock on the 0th day. What actions do you think that I can take on the very next day? Essentially, what I'm asking is, what actions make sense just after buy? I would encourage to give a short pause and try to think. It should be S and H. Let's see why. Now it cannot be buy again. This is because buying, after buying, means that we are taking multiple shares or we are holding multiple shares of the stock at the same time, which is clearly a condition of the question that it is not allowed. So this possibility is gone. Ignore also doesn't make sense after buy, because when we have bought the stock, we can either sell it the very next day or we can hold that stock. Ignore comes into picture only after selling, and we want to completely ignore that day. Now, for the same reason, I can divide this set further into two smaller sets. Ones that have S after B and ones that have H after B. Now, if my goal is to find B0 or the overall maximum in the set, I can very well safely say that it is the maximum of this and this. Let me call them M1 and M2. Make sense? Now, what is the M1 set? It is nothing but the set which definitely has the sell action on the first day. Similarly, what is this set? It is the set where the trader has the H or the hold action on the first day. Now, similar to how we define B0, let me now define S1 and H1. S1 is the maximum profit from the first day till the end, given that there is a sell action on the first day. Similarly, H1 is the maximum profit that the trader can make from the first day till the end, given that he has hold action on the first day. Effectively, what I'm saying is that the best value here, I can call this S1, and similarly the best value here, I can call it H1, as per our definition of S1 and H1. Now again, remember, our goal is to find B0, which is nothing but the overall best value in this set. At the same time, we also know that this set could either have BS type permutations or BH type permutations, because S and H are the only logical actions after B. I also know that the maximum value here is S1 and the maximum value here is H1. So I can say that if I have to calculate B0, it should be the maximum value of S1 and H1. And I have to subtract the price of the stock on the 0th day. Why? Because I have also bought the stock here. So effectively, for my two possible next moves, which is S and H, I take the maximum value and then subtract the price of the stock on the 0th day to take into account this B. Make sense? Now to summarize, I can say that B0 is maximum of S1, H1 minus price is 0. Or more generically, BI is maximum of SI plus 1, HI plus 1 minus price is N. Pretty straightforward. Now this recurrence relation is sort of the crux of this problem. I would encourage to rewind and replay the video just for improving your understanding if you see any gaps, because the thought process used in building up this relation is also going to be used for this, and this case. So let's move to the next. Now what is this set? This is a set of all the strategies where we are beginning with I or ignore on the 0th day. Now similar to how I defined B0, let me define I0, which is the maximum value or the maximum profit that I can make from the 0th day till the end, given that I have ignored the stock on the 0th day. Essentially, the maximum value in this set, let me call this I0. Now again a quick question for you. What actions do you think make sense on the day 1, given that I have ignored the stock on the day 0? It's not hard to say that the answer should be this and this. Let's see why. First, let's see this one. If I have ignored the stock on the 0th day, I can perhaps again ignore the stock on the 1st day. So this is a possibility. If I have ignored the stock on the 0th day, I can even choose to buy the stock on the next day. And so this is also a possibility. Now it doesn't make sense to hold and sell the stock on the next day after ignore, because I haven't bought anything to either hold it or sell it. So these possibilities can be eliminated. Therefore, we can say that this set contains only two types of permutations. Ones that are II at the start and ones that are IB at the start. Now, by the same reasoning that we used to derive this relationship, we can very well say that I0 is nothing but maximum of I1 and B1. And this time, we don't need to subtract this term, because on day 0, we are just ignoring that day. So we don't subtract or even add prices 0. Now let's move to the next set. The set with the sell action on the 0th day. Let me say that S0 is the maximum profit here. Now you must have very well guessed the question by now. What is the next logical action that I can take after sell? It's again not hard to convince yourself that after selling, we could perhaps buy the stock again, or we could just ignore the next day. So B and I are the next possible actions after S. So this set essentially comprises of two types of permutations. The ones that are starting with SB and the ones that are starting with SI. Now again, by the same reasoning that we have discussed above, you can say that S0 is maximum of B1, I1, and this time we also add the prices I. Because at the end of the day, we are selling on the 0th day, and hence we are gaining some money, which I am taking into account by this factor. Last but not the least, let's move to the set. This set is a set where all the strategies or all the permutations, they are beginning with H. So let me represent this by H0. Now again, what is the next logical action that I can do on the next day, given that on the previous day I have hold the stock? Not very hard to convince yourself that if you have hold the stock, then on the next day you can perhaps hold it again, or you may even choose to sell it. Hence, by the same reasoning as we discussed above, H0 is max of H1 and S1. Now once we have calculated P0, I0, S0, H0, we have got the answers to the local maximums in these sets. If we want to find the overall best value here, we take the maximum of these sets. But there is one important thing to note here. Trader cannot begin his strategy by selling the stock or by holding the stock. Pretty straightforward, right? Because he has to first buy the stock before he can sell and hold. So eventually, to find the overall max in this set, or to find our answer, we take the maximum of B0 and I0. Now let's try to solve this problem by hand. I have made 4 answer arrays to store the value of BI, II, SI and HI. It makes sense to move from right to left because our left is dependent on our right. First, let us fill the base cases. So let's solve for this first. Now there is no I plus 1 value here or any subproblem. Now what does it mean for BI for I is equal to 6? It means that what is the maximum profit a trader can make from the 6th day till the end, given that he has already bought the stock on the 6th day. That should put him in negative because he's just buying the stock and there is no other day to sell in future. So let us put minus 7 here. Now the maximum profit he can make from this day onwards, given that he has already sold the stock on this day, by similar logic, should be plus 7. Now what is the maximum profit that the trader can make from the ith day or 6th day onwards, given that he has ignored the stock here? It's nothing but 0. And same goes for whole day. Now after having solved for these base cases, let's move to our next layer. What is BI for I is equal to 5? You can see from here that it is the maximum of S6 and H6. Now what is S6? It is plus 7. What is H6? It is 0. The maximum would be plus 7. And then we subtract the prices I. So it should be plus 7 minus 15. which should be -8. Similarly, what should be the value of I5? From the equation, we can see that it is the maximum of I6 and B6. So it should be the maximum of this and this. So let's put 0 here. Similarly, what is S5? Now from this equation, we can see that it is the maximum of B6 and I6 plus the price is I. So what is B6? It is -7. What is I6? It is 0. So the maximum of B6 and I6 is 0. And let's add the prices I. So let's add 15 here. So 0 plus 15 is 15. Similarly, what is H5? It is the maximum of H6 and S6. So what is H6? H6 is nothing but 0 and S6 is +7. So the maximum is 7. Let's move to our next layer. B4. B4 is the maximum of S5 and H5. So S5 is 15, H5 is 7. The maximum is 15. And then we subtract prices I, which is 1. So 15 minus 1 is 14. Let's solve for I4. What is I4? It is maximum of I5 and B5. So what is the value of I5? It is 0. What is the value of B5? It is -8. The maximum is 0. So let's put 0 here. So let's now solve for S4. S4 is nothing but the maximum of B5 and I5. Now B5 is -8, I5 is 0. The maximum is 0. And then we add this term, price is I, which is 1. So 1 plus 0 is 1. Now what is H4? It is the maximum of H5 and S5. So H5 is 7, S5 is 15. Now what is B3? B3 is maximum of S4, H4 minus price is I. What is H4? H4 is 15. What is S4? S4 is 1. The maximum is 15. And we subtract the price of the I. So it should be 50 minus 2. Let's solve for I3 now. I3 is maximum of I4 and B4. So what is B4? It is 14. What is I4? It is 0. So let's put 14 here. Now what is S3? S3 is nothing but maximum of B4, I4 plus price is I. B4 is 14. I4 is 0. So 14 plus price is I, which should be +2. So let's put 16 here. H3 is maximum of H4 and S4. So it should be the maximum of 15 and 1. So let's put 15 here. Now what is B2? It is maximum of S3 and H3. So S3 is 16, H3 is 15. So the maximum should be 16 and we subtract price is I. So we subtract 9. So it should be 7. Now what is I2? I2 is nothing but the maximum of I3 and B3. What is I3? It's 14. What is B3? It's 13. So let's put 14 here. What is S2? Maximum of B3 and I3. So it's 14 and then plus the price on the ith day. So price on the ith day is nothing but 9. So 14 plus 9 is 23. Now what is H2, the maximum of H3 and S3, which is the maximum of 15 and 16. So let's put 16. Now what is B1? Maximum of S2 and H2 minus prices I. So it's maximum of 23 and 16 minus 3. So let's put 20 here, which is 23 minus 3. What is I1? It's the maximum of I2 and B2. So it's the maximum of 7 and 14. So let's put 14 here. What is S1? It's the maximum of B2 and I2. So B2 is 7, I2 is 14. So 14 plus 3 should be 17. Now what is H1? H1 is maximum of H2 and S2. Now let's solve for V0. V0 is max of S1 and H1. So S1 is 17 and H1 is 23. So it's 23 minus price is I. So 23 minus 8, which should be 15. What should be I0? It is maximum of I1 and B1. So B1 is 20, I1 is 14. So let's put 20 here. What is S0? S0 is maximum of B1 and I1 plus price I. So B1 is 20, I1 is 14, and the maximum is 20. And then we add the price I, which is 8. So let's put 28 here. Last, what is H0? It is the maximum of this and this, which is 23. Now what is the overall answer? It's nothing but the maximum of B0 and I0. The given input array is the price of the stock on the TI. It is the same as we discussed in the examples. This is the function which would return the maximum profit. At last, we are just printing the maximum profit. So let's begin. First, let us try to do some sanity checking here and see if this is null or if the length is 0. If this is the case, let's just return 0. If not, let's make our memoization data structures for buying, selling, holding, and ignoring. And they should be equal to the length of the input array. Let me call this sell, hold, and ignore. Okay. Now let's fill our base cases. So the last value in this array should be negative of prices I or array I. Actually, I can call this prices, so it makes more sense. Okay. Similarly, let's fill for sell, which should be just this. Now let's move from right to left. Let's move from our second last element, which is prices length minus 2 till the start, and just calculate the buy, sell, hold, and ignore using our recurrence relation that we discussed. So buy I, this should be equal to maximum of sell I plus 1 and hold I plus 1. And we subtract the ith price. Similarly, sell I should be the maximum of buy I plus 1 and ignore I plus 1. and we add the price I. Hold I should be the maximum of hold I plus 1 and sell I plus 1. Lastly, ignore I should be the maximum of ignore I plus 1 and then buy I plus 1. Eventually, let's just return the max of buy 0 and ignore 0. So let's try to run this. And there we go. It should be 20. Now let's take a look at the time and the space complexity. Now for the time complexity, it's easy to see that we are just moving from right to left and we are progressively filling the B, I, S and H areas. So in a nutshell, it's just one sweep of the array from right to left. So the time taken is order n, where n is the length of the input array. For the space complexity as well, we have just constructed 4 other separate arrays or our memoization data structures to store the BI, II, SI and HI. So it's 4 into n or effectively order n space as well. Let's now take a look at another version of a similar problem called as the buy and sell stock, but with the cool down condition. We are given the day-wise prices of the stock. So on day 0, the price of the stock is 7, day 1 it is 2, and so on. Our objective again is to find the maximum profit that we can make from this input. The constraints are, first, we should hold at most 1 share of stock at a time. In other words, we cannot hold more than 1 share of stock at a time. For example, let's say we have bought the stock on day 0 for price of 7. Then on the day 1, we cannot buy the stock again because we cannot hold 2 shares of this stock at a time. We have to sell this, let's say at this here for the value 9, and then we can buy the stock again. Second, you can make multiple transactions. So essentially, this is allowed. Buying at 7, selling, again buying at 0, selling, buying here and selling. So we have made 3 transactions here. So we can make multiple transactions. That's allowed. Lastly, we cannot buy stock on the next day if we have sold the stock on the previous day. So what does it mean? Let's say we have bought the stock here and then sold it here. Now on this very next day, we cannot buy the stock. In other words, we have a 1-day cool down period. So if you want to buy the stock, we can buy it from this here, but not this. Now this problem is actually very similar to the original problem. The only condition that is new or added here is this one. So I would highly encourage you to learn and go through the buy and sell stock original problem, and then understanding this problem, the intuition, the thought process, the implementation should be a piece of cake. Now let's move to the intuition. In order to understand the intuition for this problem, it is very important to understand the intuition of the original problem, the buy and sell stock. Once that is clear, understanding this is fairly straightforward, but with one simple change. In the interest of the time, I will avoid the detailed explanation, but at the same time, I will go over the explanation briefly. So this is the thought process that we use. First, we try to find all the possible actions that the trader can do on any given individual day. The actions can be either B, H, S, or I. There is no other possibility. So any strategy should be a permutation of B, H, S, and I. Now I have enumerated all these permutations in this superset, which effectively now contains all the possible answers. Our objective is to find that particular strategy in this superset that yields the maximum profit. Now we divide this superset into 4 subsets. The ones with the buy transaction at the start, ones with I or ignore at the start, ones with S at the start, and the ones with H at the start. Now naturally, if we find the maximum in this set and then take the overall maximum in these 4 sets, that should give us the overall maximum in the superset or our answer. Now how do we find the maximum in this set? We try to formulate things little mathematically here. We say that the maximum in this set, let us call it B0. B0 is the maximum profit that the trader can make from the 0th day till the end, given that he has bought on the 0th day, which effectively represents this set, where we are starting with B on the 0th day, and we have to find the maximum from 0th day till the end. Same story goes for I0 here, S0 here, and H0 here. Next, we ask this question to ourselves, that what can follow a B? In other words, if let's say on the day I have bought the stock, then what are the possibilities or what are the possible actions that can come on the day I plus 1? It's not hard to convince yourself that they are just 2 possible actions, and they are either you could hold the stock or you could sell the stock. We take the maximum of these 2 possibilities, then subtract the prices on the day 0 because we have bought the stock, and that gives us the overall maximum in this set. Now in the similar way, we derive these relations. Now there is one little change that we have to do in this third relationship. It is based on the condition 3 of the problem statement. The condition 3 says that we cannot buy the stock on the next day if we have sold the stock on the previous day. And therefore, after sell, buy cannot be our next action. Hence, we remove this term from our equation. So, it becomes SI as II plus 1 plus prices I. Eventually, when we find the overall maximum or our answer, we just take the maximum of B0 and I0, and we don't include S0 and H0. The reason being that on the very first day, selling and holding doesn't make sense, because in order to do so, we first have to buy the stock. Now let's try to solve this problem by hand. We'll move from right to the left because our left answers are dependent on the right answers. So let's try to fill this layer first. Now what is BI? It is the maximum of Si plus 1, Hi plus 1 minus prices I. Now there is no next layer to this, and therefore we put minus prices I or minus 5 here. Now what is II? II is the maximum of II plus 1 and Bi plus 1. Again, there is no next layer, so let's put 0 here. By similar reasoning, let's put 0 for Hi. For Si, again, there is no next layer, so let's just put prices I or plus 5. Now let's move to this layer. What is Bi? This is the maximum of Si plus 1, Hi plus 1. So it is the maximum of 0 and 5 minus prices I. So I can put minus 10 here. What is II? It is the maximum of II plus 1 and Bi plus 1. So it becomes. Now what is Si? Si is II plus 1 plus prices I. II plus 1 is 0 and prices I is 15. So let me put 15 here. Now what is Hi? Hi is maximum of Hi plus 1 and Si plus 1. So it is maximum of 0 and 5, which is 5. Now let's fill this layer. What is Bi? Maximum of Si plus 1, Hi plus 1. So this becomes maximum of this and this minus prices I. So let me put 14 here. What is II? This is the maximum of II plus 1 and Bi plus 1. So it becomes maximum of 0 and minus 10, which is 0. So let us put 0 here. What is Si? Si is II plus 1 plus prices I. So it is 0 plus prices I, which is 1. So let me put 1 here. What is Hi? Hi is maximum of Hi plus 1, Si plus 1. So it is maximum of 5 and 15. So let me put 15 here. Let us fill the next layer now. Now what is Bi? It is the maximum of Si plus 1, Hi plus 1. So it is maximum of 1 and 15 minus prices I. So let's put 15 here. What is II? Maximum of II plus 1 and Bi plus 1. So let's put 14 here. What is Si? It is II plus 1, which is 0, plus prices I, which is again 0. Let's put 0 here. What is Hi? It is maximum of Hi plus 1 and Si plus 1. So it's maximum of these two, which is 15. Let's again come to this layer. What is Bi? Max of Si plus 1, Hi plus 1. So it is max of this and this minus prices I. It should be 6. What is II? This maximum of II plus 1 and Bi plus 1. So let's put 15 here. What is Si? This is II plus 1 plus prices I. So let's put 23 here. Hi is max of this and this. So let's put 15 here. Bi is max of Si plus 1, Hi plus 1. So 23 and 15, just 23. Bi is maximum of Si plus 1, Hi plus 1 minus prices I. So Si plus 1 is 23, Hi plus 1 is 15 minus prices are. So let's put 21 here. What is II? This is max of II plus 1 and Bi plus 1. So 15 and 6 max. just 15. What is SI? It is II plus 1 plus price is I. So let's put 17. What is HI? Max of HI plus 1 and SI plus 1. So let's put 23 here. Let's come to our last layer. What is PI? Max of SI plus 1, HI plus 1. So SI plus 1 is 17. HI plus 1 is 23. The max is 23 minus 7. So let's put 16 here. What is II? Max of II plus 1, BI plus 1. So 15 and 21. So let's put 21 here. What is SI? This is II plus 1 plus price is I. So 15 plus price is I. So it should be 22. What is HI? Max of HI plus 1 and SI plus 1. So 23. Eventually, we just take the maximum of these two to find our answer. So our answer is 21. I have defined a function called as the maximum profit with cooldown, which takes in the input array and returns the maximum profit or the answer to us. I have used the input array to be the same that we were using in the examples. And eventually, I'm just printing the value for cross-checking. So let us begin. First, let me start by handling some edge cases. So I check if the prices is null or the prices length is 0. If this is the case, if the price is null or if it's empty, I just return 0 trivially. Next, let us try to declare our data structures for buy, sell, hold, and ignore. So they would be used to calculate the values at each individual steps. And they should be equal to the length of the input array. Ignore and then. Next, let us initialize our base cases. So buy should be equal to minus price is I. And let us also do this for sell. And this should be plus price is I. For hold and ignore, they are 0. So I will keep them untouched because when we initialize the array, by default, everything is initialized to 0. So they should be taken care of. Next, let us move from right to left. I will move from the second last layer because we have already filled the last layer here. So it should be prices of length minus 2 get greater than 0 and minus from this. Next, let us try to use the recursive relations that we derived. So buy I. So what are the possible actions after buy? We can sell it or we can hold it. So I'll call it sell I plus 1, hold I plus 1. I'll take the max and then subtract price is I. What about sell? After selling a stock, we can either buy it or ignore it. But according to the conditions given in the question, we cannot buy the stock the very next day after selling because there is a cool down aspect. So let us put just ignore plus price is I. Let us now fill ignore I. So what can we do after ignoring on a day? We can perhaps choose to again ignore the next day. Or we can choose to buy on the next day. Last but not the least, after holding a stock, we can choose to again hold a stock, or we can sell it off. Ultimately, let us just return the maximum of 𝗋𝗎 and ignore 0. Let's start it on this. And there we go. Let's now look at the time and the space complexity for our solution. Let's first begin with the time complexity. So in our algorithm, what we essentially did is we moved from the right of the input array to the left. And in this process, we kept on filling these individual arrays for 𝗶𝗶𝗶𝗄. So the amount or the time taken would be proportional to the length of the input array. Because for every element of the input array, we are filling 4 places. So precisely, it should be 4 into n, which is order n. Now let's talk about the space complexity. We are using 4 extra arrays that are equal to the size of the input array. So the space complexity or the extra space that we are using is again 4n, which is nothing but order n. So order n is both the time as well as the space complexity. Now in this video, let us talk about another popular TP problem that is called money change. Now there are a couple of variations of this problem, and we are looking at the first one. The problem statement is very simple. We are given coins of different denominations and an amount that we have to form with those coins. For example, we are given coin 1, coin 3, coin 5. You can assume there is an infinite supply of each category or each denomination of the coin. So we are given coins in this array, and then there is an amount that we have to form with those coins. What we have to do? We have to return the least number of coins that are needed to make that amount. It can be possible, or is it not possible? If it is not possible, then we have to return -1. So, for example, if we have to make 13 using 135, perhaps we can take 1, 1, 1, and then 5. So we have taken 2 coins of denomination 5 and 3 coins of denomination 1, and then they add up to 13. Now, how many number of coins we have used here? It is 5. Perhaps we could have just added coin 1 13 times, and we form 13. Now, how many coins we have used here? 13. Now, similarly, there are many possible ways to form 13 with these coins. We have to find the least number of coins that are needed to make that amount. So basically, out of all these possible ways, there is definitely a way which has the least number of coins used to make 13. Now we have to return that least number. Let's say if it is 3 coins or 2 coins, then we have to return 2. Make sense? Now let's take a look at the intuition for this problem. So we have to form 13 with these coins. And then we have to find that particular way which involves the least number of coins. So basically, if I am given the amount 13, let's try to think, what is the next step that I can take to make that amount 13? So I am given 13 as my initial amount that I have to make. I can perhaps choose coin 1 And then I have to make 12 because I have already chosen 1, which subtracts the value that I have to make by 1. The second possibility is I can choose 3. And the third possibility is I can choose 5. There are only 3 things possible because these are the only denominations of the coins that are given to us. So initially given 13, my first step could be I have chosen 1, I have chosen 3, or I have chosen 5. If I have chosen 1, then I have to make 12 because 12 is remaining now. If I have chosen 3, then I have to make 10 now because 10 is remaining. And if I have chosen 5, I have to make 8 now because I can subtract 5 from 13. Now similarly, we can draw the tree again here and again here. Now try to think. If perhaps someone already tells you that the minimum number of coins needed to make the amount 8, to make the amount 10, to make the amount 12 is X, Y, and Z. In other words, I already know the answers to these subproblems. Now, if I already know the answer to these subproblems, then definitely my answer to the original problem would be the minimum value amongst these. So I choose minimum X, Y, Z, and then definitely 1. Why 1? Because we have chosen either coin 1, coin 3, coin 5, which means we have picked up 1 coin, and therefore we need to add 1. So the first step, we can choose 1 or 3 or 5. Therefore, we have chosen 1 coin in the number of coins. And then the remaining subproblems would be we have to form 12 with the minimum number of coins. We have to form 10 with the minimum number of coins. We have to form 8 with the minimum number of coins. Let's say the answers to them are X, Y, Z. So the overall answer would be the minimum coins needed for X, Y, Z, the minimum value amongst these, and then plus 1. I hope it makes sense. Now I have drawn and extended the tree a little more here. So just so that you are aware of the conventions, MC means the minimum number of coins needed to make the amount. So MC13 is the minimum number of coins needed to make 13. MC8 is the minimum number of coins needed to make 8. So initially we have 13. Okay. We can choose either coin 1, coin 3, and coin 5 as the first step. If we go via this path where we have chosen the coin 1, then we have 12 as the remaining amount. And MC12 would mean the minimum number of coins needed to make 12. Also, I have added the value of 1 here because since we have chosen the coin 1 as our first step, we have added 1 to the answer, which is the number of coins. So 1 for this coin. And then what is the minimum number of coins to form the remaining amount? 12. Similarly, 1 plus 10, because 10 would be the remaining amount if we have chosen 3. And similarly 8 because it is 5 here. And 1 would stay the same because in our initial step, we are just choosing 1 coin, either of denomination 1, either of denomination 3, either of denomination 5. Similarly, we can extend this, and this below. Now, perhaps if you, let's say, extend 12 and you go via this path, then you remain with the problem of finding the minimum coins to form 9. And then you can also see the same subproblem occurs here. So if there is 10, and we chose the first path for the coin 1. So we have 9 amount remaining, 10 minus 1. And therefore the same subproblem appears. Similar observation can be made here. Where it is 12, I have chosen the coin 5. And therefore 7 is remaining. Similarly, if it is 8 and I have chosen 1, 7 is remaining. So these are the instances of overlapping subproblems. These are just a couple of instances, and if we extend the tree till the bottom, there could be many such instances. So it makes sense to use dynamic programming in this case, because we don't want to compute the same answer again and again. If let's say we go to this 9 in our implementation first, and then we go to this 9. So we don't want to compute this 9 again. We don't want to make a whole tree and then get its value, because we have already done that here, if it makes sense. So once we have got the value of 9, we just save that. And then whenever the next time we need to compute the similar answer or the similar subproblem, we just use the already saved answer. So let me just write whatever we have discussed mathematically here. So if we need the minimum number of coins needed to form the amount x, that would be the minimum number of coins needed to form x minus 1 plus 1. Second possibility, minimum number of coins needed to form x minus 3 plus 1. Third possibility, minimum number of coins needed to form x minus 5 plus 1. This is basically where we have chosen 5 as our first coin. This is where we have chosen 3 as our first coin. And this is where we have chosen 1 as our first coin. Now, one more thing to notice here is that when we calculate the answer for the amount 13, it is dependent on the answers for 12, 10, and 8. These values are lower in comparison to 13. Similarly, 12 is dependent on 11, 9, and 7. Again, these values are lower in comparison to 12. So following the same trend, we should eventually go to 0 and 1. That would be the leaf of this particular tree. And therefore, I have created an array pair that basically stores the answers to all these subproblems. So 13, the answer is stored here. 10, 12, 8, the answers are stored here. Similarly, for every particular value from 0 till the 13, this array would be storing the answers. And we very well know that the base case is quite easy to solve, which would be the value 0. The answer would be 0. And therefore, we would proceed from the left till the right, because anything in the right is dependent on some value in the left. And therefore, we will compute the left values first and then move from left to right. I hope it makes sense. Now let's try to solve this problem by hand. First, let us take a look at the base case. We have to make the amount 0 using these coins. Now basically, 0 means that there is nothing to make. And therefore, we do not have to choose any coin. And hence, we put the answer as 0 for this base case. Let's now move to the amount 1. Using this recurrence relation that we derived in the previous slide, the answer for 1 would be given by the answer for 0, which is 1 minus 1 plus 1. 1 minus 3, which is minus 2 plus 1. 1 minus 5 minus 4 plus 1. It would be the minimum amongst these values. Now, we definitely cannot make a negative amount. with these points. So we simply discard these possibilities. And therefore, the answer would be whatever the answer is for 0 plus 1. So let us put 1. Let's now move for the amount 2. Again, let us use the recurrence relation. 2 minus 1 is 1 plus 1. 2 minus 3 is minus 1 plus 1. 2 minus 5 is minus 3 plus 1. Negative amounts cannot be made. We discard these. The answer would be whatever the answer is for 1 plus 1. Let us put 2. Let's move to the amount 3. The answer would be given by the minimum of 3 minus 1, which is 2, plus 1. 2 minus 3, which is 0, plus 1. 3 minus 5, which is minus 2, plus 1. This can be discarded. Minimum of these two possibilities. So what is the answer for 2? It is 2. What is the answer for 0? It is 0. The minimum value is 0. And therefore we choose this and add 1, which is this particular case. Hence we put 1. Let's move for 4. For the amount 4, the answer would be whatever the answer is for 3 plus 1, or whatever the answer is for 1, guess what? 1 is minus 3, or whatever the answer is for minus 1 plus 1. This can be discarded. We have to see if the answer for 1 versus the answer for 3, which is smaller. Both are the same, so we can pick either of them. And therefore the answer would be 1 plus 1. Let's put 2. Let's move for the amount 5. 5 is given by the minimum of these possibilities. 4 plus 1, 2 plus 1, 0 plus 1. So 0, 2 and 4. 0, 2 and 4. Minimum is 0. We add 1. So let's put 1 here. For 6, the answer is given by minimum of 5 plus 1, or 3 plus 1, 1 plus 1. The answer for 1 is 1. The answer for 3 is 1. The answer for 5 is 1 as well. So we can choose either of them. And we add 1. And hence we can put 2. Let's move to 7. The answer for 7 would be given by minimum of these possibilities. What are these possibilities? It would be 7 minus 1, which is 6. 7 minus 3, which is 4. 7 minus 5, which is 2. Plus 1, plus 1, plus 1. Let's see if 2, 4, 6. So, which amongst them have the smallest value? All of them have the value 2. They are the same. So we can choose either of them and then we add 1. And therefore, we can put 3 here. Let's move for 8. The answer is given by minimum of these possibilities. What are these possibilities? It would be 7 plus 1. It would be 5 plus 1. It would be 3 plus 1. Or what is the minimum amongst them? 3, 5, 7. It is 1. And therefore we put 1 plus 1 as 2 here. Now let's move to 9. Now for 9, the answer is given by the minimum of the possibilities 8 plus 1, 6 plus 1, or 4 plus 1. What is the minimum? For 4 it is 2, for 6 it is 2, for 8 it is 2. So any of them can be picked and we add 1. Let's put 3 here. For 10, the answer is given by the minimum of 9 plus 1, 7 plus 1, or 5 plus 1. So 5, 7, 9. The minimum is 1. And therefore we add 1 to it. And hence we put 2. Similarly for 11, we can say that the answer will be given by the minimum of 10, 8 and 6. And the minimum is the value 2. So we put 3 here. For 12, it is given by the minimum of 11, 9 and 7. Minimum is 3. We add 1, so we can put 4 here. For 13, it is given by the minimum of 12, 10 and 8. The answer would be given. We add 1, so it becomes 3. Ultimately, since we have to form the amount 13, we return this as a final answer. Solve this problem by hand. I have created a function called as the minimum coins to make the amount. This accepts the parameters of coins and the amount. It returns the answer that we ultimately print for cross-check. I have used the same values that we were taking when we were solving the example by hand, just for simplicity. So let us try to implement this function. First, we declare the DP error to be the size of amount plus 1. Amount plus 1 because amount should be inclusive. As you can recall, when we were solving the example by hand, the DB array contained from index 0 till index 30, and therefore index 13 was included too, and therefore we add amount plus 1. Next, we initialize the base case to be 0. Now, let me run a for loop. Let me call it as the current amount. That goes from 1 and it goes till the amount. So basically what I'm doing here is I'm trying to solve for all the sub-problems that come in between. Now, the answer to all these sub-problems, for storing them, let me create a variable. Let me call it minimum coins for current amount. And at first, let me just initialize this to integer.max value. Now, let me iterate through the coins. Now, as you can recall, our recurrence relation was that we take the minimum of all these possibilities. So, minimum that we have seen so far, that's why this is the first argument. And then the possibility. The possibility would be current amount minus coins are. However, we also have to check a couple of things here. So if the current amount minus coins are, this goes negative, then we just have to discard that possibility. So basically we will only do this when this is positive. In addition, there is one more case. So basically, the amount can be made using the coins or it cannot be made using the coins. There might be such possibilities or such combinations of the input that you cannot make the amount using those coins. It's easy to think. For example, let's say you have just the supply of 2 and you have to make the amount of 3, then it's not possible. Now, if any particular current amount that is seen in this for loop, if that is not possible, then the value of that current amount would just be the integer.max value. And if it is not possible, then definitely we cannot use that sub-problem while calculating the answer to our ith problem, or basically the current amount. So what I can say here is, if the DP current amount minus coins are. If this is not equal to integer or max value, then only it makes sense to do this. Another way to think is if perhaps this is equal to the integer or max value. What does that mean? It means that this dp and this subproblem is actually not possible. So basically, the BP subproblem should be possible to solve for. In other words, it should not be -1 or integer or max value, because this is the value that would signify that in this case. So this is our comment for the second case. And the first case is pretty straightforward, that you just discard the negative possibilities. I hope it makes sense. Now, once we have computed the minimum, then what we do is we just assign it in the DP. So the answer for my current amount would be minimum coins for the current amount. Ultimately, when we exit the for loop, we return DP amount. Now, one more thing. This DP amount can also be integer or max value. Conceptually, that would mean that it is not possible to make that amount using the given combination of coins. So we check if this is integer or max value or not possible. So basically this holds true. It means it is not possible. Means we return -1. Otherwise, we can safely return DP amount. Let's try to run this and see. Should give us 3. And there we go. Now let's look at the time and the space complexity. Now in our algorithm, we just have created one extra space for an array. The size of this array is equal to the amount. And therefore, the extra space required is order amount. So the space complexity would be order amount. What about the time complexity? In our algorithm, we just have filled this array one by one. Filling every entry took us the amount of time that is proportional to the number of entries here. Because let's say we wanted to fill 3. So we calculated what is the answer for 3 minus 1. What is the answer for 3 minus 3? What is the answer for 3 minus 5? Now, the number of these entries, or the number of these possibilities rather, is directly dependent on the length of the coin setup. Basically, how many different types of coins have. So if let's say we have 3 types of coins, so filling every entry took us the time order 3, or basically 3 units, we can say. If it would have been 4, filling any particular entry, let's say this, would have taken us 4 units of time. And therefore, generically, we can say if this has the length, let's say length of coins, or let me just call it C. So filling every entry would require us to calculate the answers, or rather see the answers for C possibilities, and then choose the minimum amongst them. And therefore, filling every entry takes time, order C. Now, how many of these entries do we have? We have 13 entries, or the order amount entries. And therefore, the total complexity will be order amount into order C. Just basically order amount into C. So time complexity would be order amount into C. C is the length of part 0.